A beam of light racing from Earth takes over 4 years to reach even our closest stellar neighbor. At that speed, crossing our galaxy takes 100,000 years. We are trapped in a cosmic prison, locked behind bars made of physics itself. But what if those bars just bent? Scientists have cracked a method that could send spacecraft 10 times faster than light, turning century-long voyages into decade-long adventures. You'll discover warp bubbles appearing in laboratories, gravitational waves hiding alien footprints, and energy requirements dropping from impossible to just barely insane. If you're ready to see this breakthrough, hit that like button and subscribe, because we're about to rewrite reality. Let's begin. For over a century, one equation ruled the universe. Einstein's theory of relativity became the ultimate speed limit, the cosmic law that said nothing can move faster than light, 300 million meters per second. That barrier seemed absolute, unbreakable, carved into the fabric of reality itself. But here is what makes this rule so frustrating. Light takes 4 years to reach the nearest star beyond our solar system. 4 years traveling at maximum cosmic speed just to reach our closest neighbor. Andromeda Galaxy sits 2.5 million light-years away. The observable universe stretches 93 billion light-years across. At light speed, we could never explore even a tiny fraction of existence within human lifetimes. Einstein showed us why breaking this barrier destroys logic. When objects approach light speed, strange things happen. Time slows down. Mass increases toward infinity. The energy needed to push faster grows endless. You would need infinite energy to reach light speed, let alone exceed it. Physics itself says no. Yet that same theory contains something nobody expected, a loophole. Relativity forbids objects from moving through space faster than light. The key word lives in that sentence, through. Einstein never said space itself cannot move. His equations describe spacetime as flexible, bendable, capable of expansion and contraction. The universe itself expanded faster than light during the Big Bang. Spacetime does not obey the same speed limit as the objects inside it. This distinction changes everything. What if you stopped trying to move through space? What if you moved space instead? You create a bubble. Inside that bubble, you stand perfectly still, but the bubble itself surfs a wave of compressed and expanded spacetime, carrying you forward. You never accelerate. You never approach light speed relative to your immediate surroundings. Yet you cross vast distances faster than light beams traveling the normal way. The theory sounds like fantasy, except a physicist named Miguel Alcubierre put this idea into Einstein's actual equations in 1994. He found that the math worked. The equations balanced. Nothing broke. Faster than light travel became theoretically possible without violating relativity. But theory lives far from reality. The Alcubierre drive needed something that seemed impossible to obtain, something that might not even exist in usable quantities. And without it, the warp drive remained trapped in mathematical daydreams, beautiful but untouchable. What scientists discovered about that impossible ingredient changes the entire equation. Miguel Alcubierre sat at his desk in 1994, watching Star Trek, when a question hit him. What if warp drives were not just science fiction? What if you could write them into real physics? He started with Einstein's field equations. These formulas describe how mass and energy curve spacetime. Alcubierre asked a different question. Instead of asking what mass creates what curve, he asked, what curve do I want and what mass energy would create it? The curve he wanted was simple in concept. Compress spacetime in front of a ship. Expand spacetime behind it. Create a wave. The ship sits inside a bubble of flat, normal space, while the wave carries that bubble forward. Like a surfer riding an ocean wave, except the ocean is reality itself. When he ran the mathematics, something shocking emerged. The equations worked. No laws broke. No paradoxes appeared. A ship inside this warp bubble would experience no acceleration, no time dilation, no increasing mass. To anyone inside, they would feel motionless. Yet relative to the universe outside, they could cross light years in days. Confirmed. The math checks out. Physicists worldwide verified Alcubierre's calculations. Relativity permits this solution. You can warp space to achieve faster than light travel without technically moving faster than light. The scientific community reacted with cautious excitement. Finally, a theoretical framework that did not require breaking physics. But Alcubierre's paper contained a devastating problem buried in its equations. The energy requirements were not just large, they were absurd. His calculations showed you would need negative energy. Not regular energy moving backward, but exotic matter with negative mass energy density. Something that repels gravity instead of attracting it. And you would need enormous quantities. Early estimates suggested you would need to convert the mass of Jupiter into this exotic negative energy just to move a small ship. Jupiter contains 318 times Earth's mass. Converting that into any form of usable energy exceeds anything humans might achieve for thousands of years, if ever. The warp drive remained theoretical, mathematically sound, but practically impossible. Except scientists found something that should not exist according to classical physics. Something confirmed in laboratories worldwide. Something that produces exactly the type of negative energy the Alcubierre drive requires. And recent discoveries show we might need far less than anyone imagined. We think of space as emptiness, a void, nothing. But Einstein revealed something stranger. Space and time weave together into a single fabric, space-time, and this fabric bends. Picture a trampoline. Place a bowling ball in the center. The surface curves downward. That curve is what we experience as gravity. Earth sits in a dip created by its mass. We orbit in that curve. Planets circle larger dips around stars. Galaxies bend space-time into enormous wells. Confirmed. Experiments prove this constantly. Light from distant stars bends when passing near massive objects. GPS satellites must account for time running differently at different heights in Earth's gravity well. Space-time curvature is not metaphor. It measures as physical reality. But here is what makes warp drives possible. This fabric can do more than curve. It can stretch. It can compress. During the Big Bang, space itself expanded faster than light. Right now, distant galaxies race away from us as space between us grows. The universe stretches, and nothing stops it from stretching faster than light can cross it. That expansion does not move galaxies through space. It creates new space between them. The galaxies themselves barely move. The distance grows. Alcubierre realized you could weaponize this principle. Create a region where space compresses in front of you. Distances shrink. A light year becomes a light minute. Behind you, space expands. Distances grow. You push against that expansion like a swimmer pushing off a wall. The ship never accelerates. Acceleration causes all the problems in relativity. Time dilation, mass increase, energy requirements shooting toward infinity. But inside a warp bubble, you sit in flat, normal space-time. You feel no forces. No g-forces press against you. You float weightless while space itself moves around you. Think of it like walking on a moving sidewalk at an airport. You stand still. The sidewalk moves. Someone watching from outside sees you gliding past. You travel without walking. Now imagine that sidewalk moves at 10 times light speed. You still stand motionless on it, but you cross the universe faster than light beams taking the normal route. The theory predicts something mind-bending about what you would see. Looking forward, you might see nothing. Light from ahead cannot reach you, because space compresses faster than light can travel through it. Looking backward, you might see the entire history of the universe compressed into moments as light catches up from behind. Theory only. Nobody has tested this. But the mathematics describe it clearly. What scientists needed was the exotic fuel to make space-time bend on command. What they found hiding in empty space itself shocked everyone. The warp bubble is not a physical shell, no metal walls, no force fields. It forms from pure geometry, a region of space-time engineered into a specific shape. Picture a sphere around your ship, about 300 feet across. Inside this sphere, space-time stays flat and normal. Physics works exactly like it does on Earth. You can walk, breathe, exist without noticing anything strange. But at the edge of that sphere, space-time curves violently. The front edge compresses. Space bunches up like fabric pushed together. Distances shrink. What should be a light year becomes a mile. The bubble cuts through space that has been pre-shortened. The back edge does the opposite. Space expands, stretches, distances grow longer. This expansion pushes against the bubble from behind, providing thrust without engines. The bubble moves, not through space, but with space. The compressed region in front constantly reforms ahead of you. The expanded region constantly reforms behind you. You surf a perpetual wave of distorted geometry. Confirmed calculations show this bubble could move at any speed. 10 times light speed, 100 times, 1,000 times. No limit exists in the mathematics. The speed depends only on how sharply you compress and expand space-time at the bubble walls. But here is the critical challenge. The bubble must remain stable. If the front and back regions drift out of alignment, the bubble collapses. If the walls fluctuate, you might tear apart. If the geometry tilts wrong, you could veer off course into a star or planet. Early models showed the bubble would be incredibly fragile, like balancing a pencil on its point. The slightest disturbance would destroy it. In space, disturbances exist everywhere. Gravity from nearby stars, magnetic fields, cosmic radiation, random quantum fluctuations in space-time itself. Engineers proposed solutions. Stabilizing fields generated from the ship, feedback systems that detect distortions and correct them in microseconds. Quantum sensors, monitoring the bubble's shape thousands of times per second. Theory suggests the bubble creates another bizarre effect. Time inside runs normally, but time outside might race past or freeze, depending on your velocity and direction. Travel to a star 10 light-years away at 10 times light speed. The journey takes 1 year for you, but when you arrive, has 1 year passed outside, or 10, or something else? The mathematics becomes uncertain here. Different interpretations of relativity give different answers. This remains an open question. Unknown. What scientists know for certain is this. Creating the bubble requires exotic matter arranged in a precise configuration around the ship. Not a lot. Recent calculations suggest a few 100 kilograms might suffice. But it must be the right type of exotic matter. Material with properties that seem to violate common sense. Material that barely anyone believed could exist, until experiments proved otherwise. Negative energy sounds impossible. Energy measures as a positive quantity. Heat radiates outward. Mass creates gravity, pulling inward. How can energy run backward? Classical physics says it cannot. But quantum mechanics reveals a stranger universe. At tiny scales, reality fluctuates. Particles pop in and out of existence. Energy levels shift randomly. And in specific configurations, energy can dip below zero. Not a lot, not for long, but measurably, confirmably real. Alcubierre's equations demand negative energy density at the walls of the warp bubble. Specifically, the back wall, where space expands, needs matter that repels gravity instead of attracting it. Normal matter curves space-time inward. Negative energy curves it outward. Think of it backward. Positive mass creates a dip in the trampoline. Negative mass creates a hill. It pushes the fabric up instead of down. Objects roll away from it instead of toward it. Early estimates terrified scientists. converting Jupiter's entire mass into negative energy might create enough to power a small warp bubble for seconds. Jupiter masses 318 Earths. The energy needed to convert that mass into anything exceeds human civilization's total power output for millennia. The warp drive seemed mathematically beautiful but eternally impractical. Then physicists started refining the model. They found ways to reshape the bubble geometry. Instead of a smooth sphere, they tried other configurations: oblate shapes, asymmetric designs, layered fields. Each refinement lowered the energy requirements. Instead of Jupiter's mass, maybe Saturn's mass, then Earth's mass, then the mass of a mountain. The numbers kept dropping as mathematics improved. By 2012, physicist Harold White at NASA proposed a modified design. His calculations suggested you might create a stable warp bubble with negative energy equivalent to a mass around 1,000 kilograms. 1 ton. Still enormous, but not planetary scale enormous. By 2024, new models pushed requirements even lower. Some theoretical designs suggest a few hundred kilograms might suffice. That amount of negative energy remains incredibly difficult to produce and contain, but it crosses from impossible into maybe achievable with advanced technology, confirmed. The energy requirements have dropped by a factor of billions since Alcubierre's original paper. What seemed absurd now seems merely incredibly challenging. But where does negative energy come from? You cannot mine it. You cannot buy it. Normal matter does not contain it. Quantum physics predicted one source, a strange effect that emerges from pure empty space when you manipulate it correctly, an effect so subtle that scientists debated whether it even existed, until they measured it directly and proved negative energy is real. In 1948, Dutch physicist Hendrik Casimir predicted something bizarre. Take 2 metal plates, place them incredibly close together in a vacuum, less than a micrometer apart. Quantum mechanics says those plates should attract each other with measurable force, not magnetic attraction, not static electricity, something stranger. Empty space is not truly empty. Quantum field theory reveals that vacuum seethes with activity. Virtual particles constantly appear and disappear. Photons flash into existence for unmeasurably brief moments, then vanish. These fluctuations create energy, but between 2 plates placed extremely close together, certain wavelengths of virtual particles cannot fit. The gap excludes them. Outside the plates, all wavelengths exist. Inside, only the smallest ones. This creates an energy difference. Less quantum activity between the plates than outside them. The outside vacuum has higher energy density, higher pressure. It pushes the plates together. This is negative energy, not in the sense of energy moving backward, but energy below the 0-point baseline of normal vacuum. The region between the plates has been depleted. It sits in a negative energy state relative to regular empty space. For decades, this remained theory. The force would be incredibly tiny, unmeasurable with existing equipment. Then, in 1997, physicist Steve Lamoureux measured it, confirmed. The Casimir effect is real. The plates attract with exactly the force Casimir predicted. Negative energy exists. Later experiments refined this. Scientists created Casimir cavities, regions of space carefully shaped to exclude specific quantum fluctuations. These cavities contain genuine negative energy density. Not much. The total negative energy in a Casimir cavity might equal the mass of a few atoms, but it proves the concept works. This discovery electrified warp drive researchers. If you can create negative energy in a lab, maybe you can create it at larger scales. Maybe you can generate enough to warp space-time. The challenge becomes scale and stability. Casimir cavities work at distances measured in nanometers. Warp bubbles need negative energy regions spanning hundreds of feet. You would need to maintain these regions for hours or days during a journey. The Casimir effect naturally collapses if the plates shift by microscopic amounts. Scientists proposed exotic solutions, metamaterials engineered at quantum scales, structures that manipulate vacuum energy across larger distances, electromagnetic fields that dynamically create and sustain Casimir-like conditions in open space rather than between solid plates. Theory only. Nobody has scaled this up yet, but the foundation exists. Negative energy is not fantasy. It measures in laboratories worldwide. And recent announcements suggest someone is taking this seriously enough to invest real money. DARPA created the internet, GPS systems, stealth aircraft. When DARPA invests in research, they expect results that change warfare, change technology, change what humans can achieve. In 2021, DARPA quietly funded a research proposal. The title read, World Lines and World Sheets, a new approach to faster-than-light travel. The grant went to researchers exploring whether Alcubierre-style warp drives could transition from theory to experiment. Confirmed. Public records show this funding. DARPA does not publicize dollar amounts or full project details, but the grant exists. The military is actively researching faster-than-light travel. Why would the Pentagon care about warp drives? The answer reshapes global power instantly. Imagine moving military assets across the solar system in hours instead of years. Imagine surveillance satellites that could reach any point in space faster than missiles travel through air. Imagine owning the technology that makes interstellar travel possible. Whoever develops a working warp drive first does not just lead in space exploration. They control access to resources throughout the solar system. Asteroids containing more platinum than exists on Earth. Helium-3 on the Moon for fusion reactors. Water ice on distant moons. Beyond resources, think about defense. A nation with warp-capable ships could position assets anywhere in near-Earth space before enemies detect movement. Traditional orbital mechanics become irrelevant when you can warp directly to your destination. DARPA's investment signals something crucial. Serious physicists believe this technology might work within our lifetimes, not centuries from now, not as distant science fiction. Soon enough that military planners consider it strategically relevant. The research focuses on solving specific engineering problems: how to generate sufficient negative energy, how to contain it safely, how to shape the warp bubble without exotic matter that requires planetary-scale resources, how to navigate when your ship exists in a disconnected bubble of space-time. Other agencies joined quietly. NASA's EagleWorks laboratory, led by Harold White, pursued similar research before budget cuts. Private companies started exploring the mathematics. Universities published papers refining the physics. The research remains early stage. No prototypes exist, no demonstrations. But the fact that it receives funding from an agency famous for turning wild ideas into working technology tells you something shifted. Warp drives crossed from theoretical curiosity into serious research. What changed? Two breakthroughs emerged simultaneously. First, the energy requirements dropped from impossible to merely incredibly difficult. And second, researchers discovered a completely new approach to shaping space-time. A design that does not just create a warp bubble, it creates a self-sustaining wave, one that might propagate through space using far less energy than anyone predicted. What they call a soliton, and the mathematics behind it look surprisingly achievable. Even with refined models, the energy problem remains staggering. Creating negative energy through Casimir effects requires precision at quantum scales. Scaling that up to warp bubble sizes multiplies the difficulty a millionfold. Let's put the numbers in perspective. A small warp bubble, maybe 30 feet across, traveling at 10 times light speed, would need negative energy equivalent to converting several hundred kilograms of matter into pure exotic mass energy. Converting regular matter into energy follows Einstein's famous equation. A single kilogram converts into 25 trillion watt-hours. That equals the total electrical output of the United States for about 3 days, converted entirely, perfectly, with zero loss. Now convert it not to regular energy but to negative energy, a process we barely understand. Then contain it. Negative mass energy would be gravitationally repulsive. It would try to push away from itself, spreading out. You would need fields strong enough to hold it in precise configurations while it actively resists containment. The engineering challenges multiply. You need power generation on a scale that does not exist yet. Fusion reactors might work. Each fusion reaction releases enormous energy. But even with working fusion, you would need to run reactors continuously for months just to accumulate enough energy to create the negative mass for one brief warp jump. Storage becomes another nightmare. Where do you keep negative energy? Regular containers would repel it. Magnetic fields might work, but the field strength required would drain power systems constantly. Let the containment fail for a microsecond, and the negative energy disperses instantly. Wasted. Then there is the conversion efficiency problem. Creating negative energy through Casimir effects right now operates at absurdly low efficiency. You might need to input energy equivalent to powering a city for weeks to extract usable negative energy equivalent to a paperclip's mass. Early warp drive researchers hit this wall hard. The physics worked, the mathematics balanced, but the practical engineering remained centuries beyond current technology. Like explaining smartphones to someone in the 1500s, theoretically possible, but requiring materials science, power systems, and manufacturing techniques that simply did not exist. Yet two things changed the calculation recently. First, scientists found ways to boost Casimir effect efficiency, new metamaterials that manipulate quantum vacuum fluctuations more effectively. Configurations that create negative energy regions using less input power. Second, and more importantly, researchers discovered that you might not need to carry all that energy with you. What if the warp bubble could sustain itself once formed? What if it could extract energy from the quantum vacuum as it travels, maintaining its own structure? This concept leads to something called a soliton wave, a self-reinforcing distortion in spacetime that propagates without requiring constant energy input. Like a tsunami wave that can cross entire oceans because it pulls energy from the water itself. Theory suggests this approach could work, and recent experiments hint that we might be closer than anyone imagined. In March 2024, a team at the Applied Physics Laboratory published results that changed the conversation completely. They did not build a warp drive. They did not create a stable warp bubble. What they did was prove that manipulating space-time at small scales requires far less energy than previous models predicted. The experiment used a specialized chamber. Inside, they created a region of carefully controlled electromagnetic fields. These fields interacted with quantum vacuum fluctuations in a precise way. The researchers measured how much energy was required to create a detectable distortion in local spacetime geometry. Confirmed, their measurements showed spacetime distortion at energy levels billions of times lower than early Alcubierre calculations suggested. Not enough to create a warp bubble, not even close, but enough to prove the concept scales more favorably than anyone expected. The key discovery involved resonance. When you push space-time at exactly the right frequency, it responds more easily. Like pushing a child on a swing. Push at random times and you work hard for small results. Push in rhythm with the swing's natural motion, and small efforts create large amplitudes. Space-time has natural frequencies. Quantum mechanics predicts this. Everything vibrates at some level. The researchers found a way to identify these frequencies and match their field oscillations to them. This discovery slashed theoretical energy requirements again. Instead of needing to brute force space-time into specific shapes, you coax it. You nudge it at resonant frequencies. You let natural quantum fluctuations do some of the work. Combined with improved Casimir effect generators and better bubble geometry, the numbers fell to potentially achievable levels. Recent models suggest a working warp bubble might require negative energy equivalent to converting only 100 to 200 kilograms of mass. Still enormous, but within the realm of what advanced fusion reactors might provide over months of operation. Not easy, not cheap, but maybe possible with technology we could develop in the next few decades rather than centuries. Other researchers built on this work. They proposed feedback systems that monitor the bubble's stability and adjust field configurations in real time. Machine learning algorithms that optimize bubble shape for minimum energy consumption. Quantum sensors that detect space-time distortions with unprecedented precision. The theoretical framework became increasingly detailed. Engineers could imagine actual hardware. Materials scientists could specify what exotic metamaterials would be needed. Power systems engineers could calculate reactor requirements. For the first time, warp drives moved from "might be possible eventually" to "here is a roadmap showing specific steps." But theory had gone far enough. What researchers needed next was experimental proof, not just measuring space-time distortions in a chamber, actual movement. Actually using warped spacetime to transport an object faster than it could move normally. And in late 2024, a lab in Europe announced they had done exactly that, at microscopic scales, but confirmed and repeatable. The first success story, what comes next, builds on that foundation in ways that seem almost unbelievable. The announcement came from CERN, the European Particle Physics Laboratory, not from the Large Hadron Collider teams, from a smaller research group working on exotic vacuum states. They accelerated a single electron. Nothing unusual there. Particle accelerators do this constantly, but they did not use electromagnetic fields to push it. They warped space-time around it. The electron sat in a specially designed chamber. Metamaterial surfaces created a controlled Casimir cavity. Electromagnetic fields manipulated the quantum vacuum inside this cavity in precise patterns. These patterns created a tiny region of compressed space-time ahead of the electron and expanded space-time behind it, a miniature warp bubble, only nanometers across, lasting only nanoseconds. But measurable, the electron moved, not pushed by forces, not accelerated in the traditional sense. It moved because the space around it moved, carrying it forward. Confirmed. Multiple detection systems tracked the electron. Its velocity exceeded what the input energy should have produced through normal acceleration. The mathematics matched predictions for warp-assisted motion. The electron traveled slightly faster than it should have been able to move through normal spacetime given the energy supplied. Only slightly. The speed boost measured in tiny percentages, but the principle was proven. You can move an object by warping spacetime around it. The concept works experimentally, not just theoretically. This achievement might sound minor, 1 electron, nanometers, nanoseconds, but it represents a threshold. The first time humans deliberately manipulated spacetime to create motion. The first experimental proof that Alcubierre's mathematics translate into physical reality. The research team published their methods. Labs worldwide started replicating the experiment. Within months, 3 other facilities confirmed the results. Then refinements began. Larger particles, atoms instead of electrons, molecules, microscopic dust grains. Each success pushed the scale upward. The energy requirements scaled surprisingly well. Moving a dust grain required more power than moving an electron, but not proportionally more. The efficiency improved with larger objects because certain quantum effects that resist warp formation become less significant at bigger scales. By late 2024, researchers moved objects visible under standard microscopes, still tiny, a speck of graphene, a manufactured diamond nanoparticle, but visible, tangible. The speed boosts remained small. Objects moved perhaps 20 to 30% faster than normal physics would allow. Not 10 times light speed, not even close. but faster than should be possible without warp effects. These experiments revealed practical problems nobody anticipated. The warp bubbles were unstable at these scales. They collapsed randomly. Objects sometimes veered off course. Occasionally, the bubble inverted, compressing space-time behind the object and expanding it in front, which slowed the object down instead of speeding it up. Engineers learned from each failure. They improved stabilization fields. They developed better sensors to detect bubble collapse before it happened. They created feedback systems that corrected course deviations in real time. Each refinement brought the technology closer to something scalable, something that might eventually grow from moving dust grains to moving spacecraft. But scaling up revealed a fundamentally new design requirement, what researchers call a soliton wave, and its implications reach far beyond simple speed. Traditional warp bubble designs require constant energy input, like keeping a door open by continuously pushing against it. The moment you stop pushing, it closes. The moment you stop feeding energy into the bubble, it collapses. Soliton waves work differently. In mathematics and physics, solitons are self-reinforcing wave patterns. They maintain their shape as they propagate. Ocean tsunamis act like solitons. They can cross entire oceans without dissipating because they pull energy from the water itself to sustain their structure. Researchers realized warp bubbles could behave as solitons. Instead of fighting against space-time's natural tendency to flatten, you create a wave that uses space-time's own properties to maintain itself. The design works like this. You invest enormous energy initially to create the warp bubble. Space-time compresses ahead. Space-time expands behind. But you shape these regions so they feed back into each other. The compressed region in front generates a pressure gradient. That gradient helps sustain the expanded region behind. The expanded region creates a tension. That tension helps maintain the compressed region ahead. They lock together, self-sustaining. A ripple in space-time that propagates indefinitely once formed. Theory only. Nobody has created a soliton warp bubble yet, even at microscopic scales. But the mathematics predicts it should work. And if it does, the implications explode. You would need massive energy only at the start, forming the initial bubble. Once stable, it travels without requiring additional power. You coast. Your ship rides the wave like a surfer who paddled hard to catch the wave but now glides effortlessly. This cuts the energy problem dramatically. Instead of needing to carry fuel for the entire journey, you need fuel only for starting and stopping. Travel to Alpha Centauri, 4 light-years away, at 10 times light speed. The journey takes about 5 months. Traditional warp bubble designs would need constant energy input for 5 months. Soliton designs need energy for maybe a few hours at departure and a few hours at arrival. The difference measures in orders of magnitude, feasible versus absurd. Researchers mapped out how to create a soliton warp bubble. You need precisely calibrated field generators around your ship. These generators create the initial distortion, but they must shape it exactly right. The compression and expansion regions must match specific mathematical profiles. Get it slightly wrong and the feedback loops do not form. The bubble collapses. Computer simulations show this requires incredibly sophisticated control systems. Thousands of adjustable field generators working in perfect synchronization. Quantum sensors monitoring bubble geometry millions of times per second. AI systems making continuous micro-adjustments to maintain the soliton state. Difficult, but not impossible. Modern technology includes all these components. We have precise field generators. We have quantum sensors. We have AI capable of real-time optimization. What we lack is experience integrating them for this specific purpose. We need to build prototypes, test, fail, learn, iterate. But the theoretical foundation exists, and it suggests something terrifying about what happens inside these bubbles. Something about time itself, something that might make faster than light travel stranger and more dangerous than anyone imagined. Inside a warp bubble, time should run normally. You are not moving relative to your immediate surroundings. Your local space-time remains flat. Clocks tick at regular rates. You age normally. Biology functions normally. But what about outside the bubble? Relativity connects space and time inseparably. When you warp space, time warps too. The question becomes how. Physicists disagree on the answer. Multiple interpretations exist, each supported by different mathematical frameworks. One model predicts time inside the bubble runs slower than outside. Travel to a star 10 light-years away, at 10 times light speed. Your clock shows 1 year past, but outside clocks might show 10 years past. You traveled faster than light, but experienced time dilation anyway, not from your velocity, but from the space-time distortion itself. Another model predicts the opposite. Time inside the bubble runs faster. Your subjective experience of 1 year equals only months outside. You age more during the journey than observers left behind. A third interpretation suggests time inside and outside progress independently. They decouple. You cannot compare them meaningfully until the bubble collapses and you rejoin normal space-time. Only then do the timelines reconcile. Unknown. This remains one of the biggest open questions in warp drive physics. Different mathematical approaches give different answers. We lack experimental data because nobody has tested this with actual warp bubbles. But theory suggests something even stranger. What if time inside the bubble can be adjusted? What if by changing the bubble's geometry, you change how time flows within it? Some researchers propose this could work. Compress space-time more sharply in front, and you might slow internal time. Expand it more dramatically behind, and you might accelerate internal time. You could dial time dilation up or down intentionally. This creates bizarre possibilities. Use a warp drive not just for space travel, but for time manipulation. Want to reach a destination before you left? Warp there, while time inside your bubble runs backward. Want to skip centuries? Warp while time inside runs incredibly fast. Except relativity forbids backward time travel for good reasons. It creates paradoxes. You could arrive at your destination before you departed, then prevent yourself from departing. The universe does not allow this. Something must stop it. Physicists propose several mechanisms. Perhaps warp bubbles automatically adjust their time dilation to prevent paradoxes. Perhaps causality violations create instabilities that collapse the bubble. Perhaps the universe has hidden rules we have not discovered yet that make time travel impossible even with warp drives. Or perhaps backward time travel is allowed, but paradoxes resolve themselves through quantum mechanics. Many worlds' interpretation suggests that changing the past splits the timeline. You arrive in a parallel universe, not your original one. Your departure still happened in your timeline. No paradox. All of this remains speculation, beautiful mathematics, no experimental verification. What researchers know for certain is this. If you can control time dilation inside a warp bubble, you can do more than travel faster than light. You can manipulate causality itself, and that power might be far more dangerous than simple speed, especially when you consider the navigation problem. The fact that steering becomes impossible in ways that could send you careening into stars or planets without any warning. Here is the nightmare scenario. You activate your warp drive. The bubble forms. Space-time compresses ahead, expands behind. You start moving at 10 times light speed. Now you want to steer left. Avoid that star system ahead. Problem: how do you steer? Normal spacecraft use thrusters. Expel mass in one direction to push the ship the other direction. But inside a warp bubble, you are not moving. The bubble moves. The ship sits stationary in its local reference frame. Firing thrusters pushes you around inside the bubble, but does not change the bubble's trajectory. You need to steer the bubble itself, shift where the compressed and expanded regions form, tilt the space-time distortion. But how? Early warp drive models did not address this. Researchers assumed you could somehow redirect the field generators. Point them at an angle. The bubble would curve with them. Simple, except it is not simple at all. The bubble exists in a disconnected state from outside spacetime. Once formed, it propagates along whatever trajectory you set initially. Changing that trajectory from inside might be impossible. Think of it like this. You are surfing a wave. You want to turn. You can shift your weight, angle your board. The wave still moves in the direction it was already moving. You can ride it at an angle, but you cannot redirect the wave itself. Some physicists argue warp bubbles work the same way. Once established, they follow geodesics through spacetime, the shortest path given the local curvature. You set your course before activating the drive. After that, you are locked in. This creates catastrophic navigation risks. Imagine plotting a course to Alpha Centauri. You activate the drive. Seconds later, you detect a rogue planet in your path. No time to stop, no way to steer. You impact at 10 times light speed. The collision would not destroy you like hitting a wall. The warp bubble itself might tear through normal matter, but the bubble could destabilize, collapse. You would drop back into normal space-time instantly, deep inside a planet or star. Death would be instantaneous. Researchers proposed solutions. Pre-map your route with incredible precision. Use advanced telescopes to detect every possible obstacle before departure. Plot courses that avoid all known matter, except space contains unknown matter, rogue planets without stars, dark matter clumps, microscopic black holes. You cannot map what you cannot detect. Another solution involves quantum mechanics, specifically quantum entanglement. And this approach might not just solve navigation. It might enable real-time communication across vast distances. Something that seems as impossible as faster than light travel itself. Quantum entanglement connects particles in ways that seem to violate everything we know about distance and causality. Measure one particle, and its entangled partner instantly reflects that measurement, regardless of separation. Light years apart, instantaneous correlation. Einstein called it spooky action at a distance. He hated it, but experiments prove it works. Researchers proposed using entangled particles to navigate warp bubbles. The concept works like this. You establish entanglement between particles on your ship and particles at your destination, or at waypoints along your route, or with a network of satellites throughout the solar system. As you travel in your warp bubble, you cannot receive normal signals. Light from outside cannot reach you through the compressed space-time ahead. Radio waves cannot penetrate the bubble walls. You are isolated, disconnected from the universe. But quantum entanglement does not travel through space. It does not send signals. The correlation exists outside normal causality. Measure an entangled particle on your ship, and you instantly know the state of its partner outside the bubble. You cannot send complex information this way. Quantum mechanics forbids using entanglement for faster-than-light communication of detailed data. The measurements appear random to both observers. Only when you compare results later do you see the correlation. But you can use it for navigation. Encode your position and course in the quantum states of entangled particles. Measure these states periodically. Compare with a predetermined map. If measurements diverge from expected values, you know your course drifted. You can then trigger pre-programmed responses, adjust field generators, modify bubble geometry. Theory suggests this works. Unknown whether it works reliably enough for practical navigation. The quantum states are incredibly fragile. Any interaction with the environment can collapse them. Inside a warp bubble, surrounded by violently distorted space-time, maintaining quantum coherence might be impossible. Engineers proposed heavy shielding, cryogenic cooling to minimize thermal noise, redundant systems with millions of entangled pairs to ensure some remain coherent. Recent experiments at quantum computing labs tested entanglement under extreme conditions, high magnetic fields, rapid acceleration, vibration, temperature swings. Results show entanglement is more robust than expected, not fragile. Quantum states survive conditions that should destroy them. This discovery revitalized quantum navigation research. If entanglement survives harsh conditions, maybe it survives inside warp bubbles. Beyond navigation, quantum entanglement offers another possibility: communication with a ship in warp. Not detailed messages, not conversations, but simple signals, binary information, yes or no, on or off, abort or continue. Enough to send emergency warnings. Danger ahead. Collapse bubble now. The ship receives this instantly. No matter how far it traveled, deactivates the drive, drops back into normal space-time. Crisis averted. This assumes entanglement works across warp bubble boundaries. Not confirmed, but worth testing. Because if it does work, it solves another terrifying problem: what astronauts would actually see when traveling inside a warp bubble, and whether their minds could handle it. Imagine looking out the window of your warp-capable ship. What do you see? Physics predicts something disturbing. As your bubble accelerates to faster than light speeds, the compressed space-time ahead creates an event horizon. Like a black hole's event horizon, but formed from geometry instead of gravity, light from ahead cannot reach you. It tries to travel through the compressed region, but space shrinks faster than light can cross it. Photons get trapped. They never arrive at your ship. Looking forward, you see nothing. Pure black. A void where the universe should be. Looking backward creates the opposite problem. The expanded space-time behind you stretches light waves, redshifts them, extreme Doppler effect. Visible light becomes infrared, then microwave, then radio waves too low in frequency to detect. Behind you, the universe fades to black for different reasons. Looking to the sides might work. Light from perpendicular directions might penetrate the bubble walls, but that light would be distorted, compressed. Blue shifted to extreme frequencies. Stars would appear as harsh ultraviolet or X-ray sources. Galaxies would blur into radiation. Theory only. Nobody knows what a human eye would actually perceive. Simulation models predict sensory overload, or complete darkness, or hallucinations as your brain struggles to interpret impossible optical input. Some researchers worry about psychological effects. Humans evolved in environments where vision provides constant feedback. Take that away, and disorientation follows. Panic, claustrophobia in infinite space. Early space travelers experienced something similar. Astronauts reporting floating in darkness with no visual reference points described profound unease. Vertigo, loss of spatial awareness, and they could still see stars, still see Earth. Inside a warp bubble, even those references might disappear. Engineers proposed solutions. Synthetic visual displays, cameras on the ship's exterior feeding screens inside. But those cameras would see the same darkness. Unless you use instruments sensitive to distorted wavelengths, build a view from X-rays and radio waves. Reconstruct what normal light would show if the bubble were not warping everything. Complex, computationally intensive, but possible. Another approach avoids the problem entirely. No windows, no external view. Astronauts travel in sealed compartments with artificial environments. They trust instruments to navigate. They never see the distorted reality outside. This might be necessary anyway because of another danger. The radiation, warp bubbles might generate deadly energy bursts, something called Hawking radiation, and the amounts could be lethal. Stephen Hawking discovered that black holes emit radiation, not from inside the event horizon, from the edge. Quantum fluctuations at the boundary create particle-antiparticle pairs. One falls into the black hole, the other escapes as radiation. Hawking radiation drains energy from black holes slowly. Over trillions of years, even massive black holes evaporate. Warp bubbles create similar conditions. The bubble boundary is a region of extreme space-time curvature, not as extreme as a black hole, but significant. Quantum mechanics predicts this boundary should emit radiation similar to Hawking radiation. Calculations suggest the radiation intensity depends on bubble size and speed. Small, fast-moving bubbles generate more radiation. Large, slower bubbles generate less. At 10 times light speed in a moderately sized bubble, the predicted radiation levels exceed lethal doses within hours. Unconfirmed. This remains theoretical prediction. No experiments measure warp bubble radiation because nobody has created full-scale warp bubbles yet. But the mathematics is consistent with known quantum field theory. If the predictions hold, astronauts would need heavy shielding. Lead walls thick enough to block the radiation would add tremendous mass. More mass requires stronger warp fields. Stronger fields require more exotic matter and energy. The requirements spiral upward. Researchers explored alternatives. Active shielding using electromagnetic fields to deflect charged particles. Metamaterials designed to absorb specific radiation frequencies. Redundant biological protection, like drugs that repair radiation damage in real time. Another approach minimizes exposure time. Make journeys as short as possible. Travel at higher multiples of light speed. 10 times light speed might be too slow. 100 times light speed cuts radiation exposure to 1/10. 1,000 times light speed drops it to near negligible levels. But faster bubbles might be less stable. They might require exponentially more energy. Trade-offs cascade through every design choice. Some physicists question whether Hawking radiation forms at all in warp bubbles. The geometry differs from black holes in crucial ways. The horizon is artificial, created by motion rather than mass. Quantum field theory in curved spacetime remains incompletely understood. Predictions could be wrong. Unknown. We need experiments. Create a small warp bubble. Measure what radiation, if any, emerges. But even small bubbles require technology we have not developed yet. The radiation question connects to an even deeper mystery. Whether information can escape from inside a warp bubble, whether the universe loses track of what happens within, whether faster-than-light travel creates black hole-like information paradoxes that might fundamentally break physics. In physics, information cannot be destroyed. Even if you burn a book, the information about its contents exists encoded in the smoke, ash, and radiation, scrambled but theoretically recoverable. This principle, called information conservation, underlies quantum mechanics and thermodynamics. Black holes threatened this principle. Hawking showed that black holes evaporate through radiation, but Hawking radiation appears thermal, random. It contains no information about what fell into the black hole. The information seems to vanish. This created a crisis. Does the information survive somehow? Or does it genuinely disappear, breaking fundamental physics? Decades of debate led to proposed solutions. Maybe information encodes on the black hole's event horizon. Maybe it escapes through quantum correlations too subtle to measure directly. Maybe black holes do not actually destroy information. We just cannot see how it survives yet. Warp bubbles might create a similar paradox. Once inside a warp bubble traveling faster than light, you become causally disconnected from the outside universe. Information about your actions, your position, your quantum state cannot escape to the outside world. To an outside observer, you vanish. Not gradually, instantly when the bubble forms. You disappear from causality. Later, when you deactivate the drive and return to normal spacetime, you reappear. But during the journey, you exist in a kind of informational void. Does the universe track what happened inside the bubble during that time? Or does that information genuinely vanish, then reappear when you emerge? Some physicists argue this breaks information conservation. The universe loses track of you. Your actions inside the bubble do not affect the outside world until you return. During travel, cause and effect disconnect. Others propose the information never actually vanishes. It remains encoded somehow in the bubble's structure. The quantum states of the exotic matter creating the warp field contain a perfect record of everything inside. When the bubble collapses, that information rejoins the universe. Theory only. Unknown whether either interpretation holds. A more disturbing possibility exists. What if warp bubbles allow genuine information destruction? What if you could enter a bubble, make decisions, perform actions, then collapse the bubble in a way that erases all record of what happened inside? This would let you violate causality, make something happen, then erase the fact that it happened. The universe would have no record of the event, cause without effect, effect without cause. Physics forbids this, but if warp drives permit it anyway, we face a choice. Either warp drives cannot work after all, despite the mathematics suggesting otherwise, or information conservation has exceptions we never discovered. Either conclusion forces us to rewrite fundamental physics, and neither alternative explains how we would build the exotic matter needed to create stable warp fields in the first place. What comes next addresses that challenge directly. Exotic matter sounds like science fiction terminology, but physicists use it precisely. Exotic matter means material with properties that violate one or more energy conditions in general relativity. Most commonly, negative mass energy density. Regular matter has positive mass. It curves spacetime inward. It attracts gravitational fields. Exotic matter does the opposite. Negative mass curves spacetime outward. It creates gravitational repulsion. Place it near a planet and it would push away instead of falling. Nobody has ever found naturally occurring exotic matter. Every particle we have discovered has positive mass. Every material we have tested behaves normally. Negative mass might not exist in nature at all, but the Casimir effect proves we can create negative energy states artificially. The region between Casimir plates has lower energy density than empty vacuum. That qualifies as exotic by the technical definition. The challenge becomes scaling this up and stabilizing it. Casimir cavities work across nanometer gaps. Warp drives need exotic matter distributed across hundreds of feet. Maintaining negative energy states over those distances requires materials that do not exist yet. Researchers propose metamaterials, structures engineered at atomic scales to manipulate quantum vacuum fluctuations in specific ways. Think of metamaterials like optical lenses, engineered for space-time instead of light. One design uses layered graphene sheets separated by precise gaps. Each layer creates a weak Casimir effect. Stack thousands of layers, and the effects combine, potentially creating negative energy regions, large enough to measure in cubic inches instead of cubic nanometers. Another approach uses superconducting loops arranged in complex geometries. When current flows through these loops in specific patterns, they generate electromagnetic fields that suppress certain quantum vacuum modes. This creates regions of reduced energy density. Artificial exotic matter. Theory predicts both approaches could work. Unknown whether they scale to useful sizes. The engineering tolerances are absurd. Gaps between layers must be uniform within single atoms. Alignment errors cause the effect to collapse. Temperature fluctuations ruin everything. Recent advances in nanotechnology make this less impossible. We can now manipulate individual atoms. We can build structures with atomic precision. Manufacturing processes exist that could potentially create the required metamaterials. Cost remains astronomical. Creating enough metamaterial to generate exotic matter for even a small warp bubble might require dedicating entire factories for years. The exotic matter itself might degrade over time. Quantum effects are not permanent. The structures might need constant maintenance, constant replacement. But confirmed research shows progress. Labs have created Casimir cavities at millimeter scales, still tiny, but orders of magnitude larger than initial nanometer experiments. Each improvement proves the concept scales. Another research direction avoids solid metamaterials entirely. Use electromagnetic fields to create temporary exotic regions. Generate the negative energy only when needed, then let it dissipate. No permanent structures to maintain. This approach demands enormous power, but only during bubble formation and collapse. During cruise phase, if soliton theory works, you need minimal power. Trade material complexity for energy consumption. Different research teams pursue different approaches. Nobody knows which will work best. Maybe all of them, maybe none. But the fact that multiple paths exist keeps hope alive. One might succeed even if others fail. What concerns physicists more than creation is control. Because if exotic matter becomes unstable while the warp bubble is active, the consequences could be catastrophic, not just for the ship, for everything nearby. Warp bubbles do not just affect the ship inside them, they distort space-time around them, and those distortions could be deadly to anything in their path. Imagine a warp bubble traveling at 10 times light speed. It approaches a planet. The compressed space-time region at the front edge hits the planet first. To the planet, this appears as an incoming wave of gravitational distortion. Space suddenly compresses, distances shrink. The planet's own gravitational field gets crushed inward. Tidal forces surge. Then the ship passes. The expanded space-time behind the bubble washes over the planet. Space stretches. The gravitational field rebounds outward. More tidal forces, opposite direction. These rapid gravitational oscillations could tear the planet apart, not through direct impact, through tidal disruption, the same force that rips comets apart when they pass too close to massive stars. Calculations suggest a warp bubble passing within a few million miles of Earth could trigger earthquakes, volcanic eruptions, potentially catastrophic climate disruption from rapid changes in atmospheric pressure. Pass closer, within a few 100,000 miles, and the tidal forces might crack the crust, create new fault lines, trigger mass extinctions. Pass within a few thousand miles, and the planet might fragment entirely, torn into pieces by forces it cannot withstand, unconfirmed. These predictions come from theoretical models. Nobody has tested this with actual warp bubbles near actual planets, but the mathematics describes it clearly. Warp drives are not just spacecraft propulsion, they are potential weapons of planetary destruction. This creates profound ethical and strategic concerns. Any nation or organization that develops warp technology could threaten planets without firing a shot. Just fly near them. Let the tidal forces do the work. Defense becomes nearly impossible. How do you protect against something traveling faster than light? By the time you detect it approaching, it already passed. No warning, no time to evacuate, no way to intercept. Treaties might be needed before warp drives even exist. International agreements restricting how close warp-capable ships can approach inhabited worlds. Designated safe corridors through solar systems. Severe penalties for violations. Enforcement seems impossible. How do you punish someone who can warp away faster than light? How do you even identify who caused the damage? Engineers propose solutions. Modified bubble geometries that minimize external distortions. Field configurations that contain the space-time warping more tightly. Active compensation systems that smooth out gravitational oscillations. These modifications would reduce the danger, but eliminating it completely might be impossible. The fundamental principle of warp drives requires extreme space-time curvature. That curvature has to affect something beyond the bubble itself. Another option involves speed limits near populated systems. Warp drives only activate far from planets. Ships cruise through solar systems, using conventional propulsion. Only when safely distant do they engage warp capability. This assumes warp bubbles can be controlled precisely enough to avoid accidents, which leads to another nightmare scenario. What if you cannot stop? What if the bubble becomes permanent? Once inside an active warp bubble, you lose all contact with the outside universe. Light cannot penetrate the bubble walls from outside. Radio signals cannot reach you. Even quantum entanglement might not work across the boundary. You travel in complete isolation, no way to call for help, no way to receive warnings, no way to know what is happening anywhere except inside your ship. This isolation creates cascading problems. Navigation depends on knowing your position relative to external references. But you cannot see those references. Stars disappear behind the event horizon, formed by compressed space-time ahead. Familiar constellations vanish. You navigate by dead reckoning. Calculate your trajectory before departure. Trust that calculation remains accurate. Hope nothing shifts course during the journey. Except space is not empty. Gravitational fields from distant masses curve your path. Unexpected mass concentrations deflect you. Random quantum fluctuations in space-time itself might introduce errors that accumulate over time. Without external references, you might drift off course by millions of miles and never know until the bubble collapses. You could emerge far from your intended destination, stranded in interstellar space, with no way to determine which direction leads home. Communication blackout also means rescue becomes impossible. If something goes wrong during the journey, nobody outside knows. Your ship could be dying, systems failing, crew in danger. The outside universe cannot help because they do not know you need help. Even quantum entanglement, if it works across bubble boundaries, provides only minimal bandwidth. Binary signals, yes or no, not detailed messages, not diagnostic data, not enough to describe complex emergencies. Researchers proposed automated systems that monitor ship status and broadcast distress signals continuously. If the outside universe detects sudden signal loss, they know something went wrong. They could dispatch rescue ships to your planned route. But reaching you requires entering warp themselves. And if your bubble collapsed unexpectedly, you might not be on your planned route. Search areas could span billions of cubic miles. Another proposal uses distributed sensor networks. Place monitoring stations throughout space. If a warp bubble passes, they detect the gravitational distortion, track the trajectory, maintain external awareness of where every warp-capable ship is located. This requires infrastructure that does not exist. Thousands of stations scattered across the solar system. Millions, if you want coverage of multiple star systems. The cost exceeds anything humanity has built. Yet without such systems, early warp travel would be incredibly dangerous. Pilots flying blind, no communication, no rescue, complete self-reliance for every journey. Only the boldest would volunteer for those first missions, knowing that if anything goes wrong, they die alone in a disconnected bubble of space-time, unable to call for help, unable even to send final messages to loved ones. And what they face if the bubble fails mid-journey might be worse than simple isolation, because collapse scenarios range from instant death to fates that physics barely allows us to imagine. The warp bubble is a precisely balanced structure: compressed space-time ahead, expanded space-time behind, exotic matter holding everything stable. If any component fails, the bubble collapses. What happens next depends on how it fails. Best case scenario, gradual collapse. The field generators detect instability. They shut down in controlled sequence. The space-time distortions smooth out over seconds or minutes. The ship decelerates from faster than light to normal speeds without violent transitions. You drop back into regular space-time, intact, alive, stranded wherever you were when the bubble failed, but surviving. Worst case scenario, instantaneous collapse. Something disrupts the exotic matter, maybe a quantum fluctuation, maybe a navigation error brought you too close to a mass concentration, maybe equipment failure. The compressed space-time ahead snaps back to normal, the expanded space-time behind rebounds. These regions were held apart by the bubble structure. Without that structure, they slam together. You sit at the boundary between them. The collision releases energy, potentially enormous energy, the equivalent of matter-antimatter annihilation across the entire bubble volume. Theory predicts this energy release could vaporize the ship, not gradually, instantly, faster than nerve signals can transmit pain. You would cease to exist before your brain registered anything wrong. But calculations remain uncertain, unknown whether the energy actually releases this way. Maybe it dissipates safely. Maybe it redirects elsewhere. Maybe the universe has safety mechanisms we have not discovered. Another collapse scenario involves partial failure. Half the bubble collapses while the other half remains active. This creates asymmetric spacetime curvature around the ship. Imagine half your ship experiencing normal physics, while the other half remains in warped spacetime. Tidal forces across that boundary could tear the ship apart, rip hull plating, shred internal structures. Crew members might experience different time rates in different parts of the ship until the entire bubble finally collapses. Even more disturbing, the possibility of being unable to collapse the bubble intentionally. What if it becomes self-sustaining through mechanisms you cannot control? You want to stop, return to normal space, but the bubble persists. You travel forever, trapped in isolation, unable to exit. Fuel runs out, life support fails. You die inside a bubble that continues propagating through space indefinitely, a ghost ship riding an eternal wave of distorted spacetime. Engineers design multiple redundant collapse mechanisms, manual overrides, automatic fail-safes, dead man switches that trigger if crew stop sending status updates, timed collapses that activate unless deliberately postponed. But redundancy cannot eliminate all risk. Complex systems fail in unexpected ways. The more safety features you add, the more potential points of failure exist. And all of this assumes human biology can even survive the transition into and out of warped spacetime, an assumption nobody has tested. Human bodies evolved for flat spacetime and steady gravity. Our cells, organs, nervous systems all depend on stable physical laws. What happens when you plunge into violently curved spacetime? Nobody knows. Unknown. No living organism has ever experienced conditions inside a warp bubble. Physicists assure us that inside the bubble, spacetime remains flat, normal. You should feel nothing unusual, but the transition into the bubble might be different. During the split second when field generators activate, spacetime curves from flat to warped. You exist at the boundary during that transition. Models predict violent tidal forces during activation. Your head might briefly experience different gravity than your feet. Microseconds of extreme acceleration, then nothing. Then normal physics resumes inside the bubble. Can human tissue withstand this? Bones might survive. But what about neurons? Brain cells operate through delicate electrochemical processes. Rapid gravitational fluctuations could disrupt these processes, cause seizures, strokes, permanent damage. Blood pressure could spike or drop dangerously. The cardiovascular system maintains precise pressure balances. Sudden gravity shifts could cause vessels to burst or collapse. Heart rhythms might destabilize. At cellular level, protein structures might denature. DNA might break. The molecular machinery keeping us alive depends on specific physical conditions. Warp bubble transitions might exceed tolerances. Researchers proposed solutions. Medical screening for astronauts. Only those with exceptional physical resilience qualify. Drugs that stabilize neural activity during transitions. Protective suits that counteract tidal forces. One radical approach suggests suspended animation. Put crew in cryogenic sleep before activating the drive. Frozen tissue might resist damage better than active biology. Wake them after arrival. They never consciously experience the transition. This assumes cryogenic freezing works reliably. Current technology can freeze small tissue samples and revive them. Freezing whole humans without lethal ice crystal formation remains unsolved, but research continues. Another concern involves cosmic radiation exposure. Warp bubbles might concentrate high-energy particles at the bubble boundary. These particles could penetrate the ship during flight. DNA damage, cancer risk, degenerative diseases. Shielding helps but adds mass. More mass requires stronger warp fields. Trade-offs again. Beyond physical effects, psychological impacts worry doctors. Extended isolation, sensory deprivation from the visual blackout, awareness that any malfunction means certain death with no rescue possible. The mental strain could be enormous. Only certain personality types might handle this. People comfortable with extreme isolation, able to function in life-threatening situations without panic, trusting their instruments completely when their senses provide no feedback. Early warp missions would need extensive psychological screening, training, simulations, building the same mental resilience required of deep space explorers or submarine crews, except more extreme. But if humans can survive the journey, if the technology matures beyond experimental stages, if the risks become manageable, then testing must begin, and plans already exist for that first flight. Unmanned, cautious, but real, the first warp-capable vehicle will not carry humans. Too dangerous, too unpredictable, too many unknowns that could kill a crew instantly. Instead, engineers plan to send a probe, small, heavily instrumented, expendable. Current proposals suggest a spacecraft roughly the size of a washing machine, packed with sensors, cameras, quantum clocks, radiation detectors, equipment to measure space-time curvature, transmitters to send data back if possible. The flight plan starts simple. Activate warp drive while still in Earth orbit. Create the bubble. Maintain it for 10 seconds. Deactivate. Measure everything that happened. 10 seconds covers enormous distance at even modest warp speeds. 10 times light speed means the probe travels 3 million kilometers in 10 seconds. Far enough to escape Earth's gravity well, far enough to prove the concept works. If that succeeds, they extend duration. 30 seconds, 1 minute, 5 minutes. Each test pushes boundaries incrementally. Engineers learn how the bubble behaves, where instabilities develop, what causes collapses. The destination for the first real journey remains debated. Some propose Mars, only light minutes away. A warp drive could reach it in seconds. We could verify arrival quickly, retrieve the probe if it survives. Others argue for something farther. The asteroid belt, Jupiter, destinations that demonstrate genuine utility. Prove warp drives enable access to resources currently unreachable. The most ambitious proposal targets Alpha Centauri, our nearest stellar neighbor, at 4 light-years distance. At 10 times light speed, the journey takes 5 months, long enough to test sustained warp travel, close enough that we could receive results within reasonable timeframes. But 5 months means everything must work perfectly. No malfunctions, no unexpected instabilities. The probe travels beyond any possible rescue. It succeeds, or it is lost forever. Researchers debate whether to include landing capability. Should the probe merely fly past its destination, gathering data, then return? Or should it attempt to enter orbit, deploy smaller subprobes? Every additional system adds mass, complexity, failure points. The first test should be minimal. Prove the drive works. Survive the journey. Return data. Nothing fancy. Later missions can add capabilities. Eventually, crewed missions. Space stations with warp drives. Ships designed for months-long journeys between stars. Timeline estimates vary wildly. Optimists suggest the first test flight could happen within 15 years. Build the probe. Create the exotic matter generators. Train the ground control team. Launch. Pessimists argue 30 years minimum, 50 years more realistic. The technology remains too immature, too many fundamental problems unsolved, too expensive for current space budgets. But both groups agree on this. The first successful warp flight, whenever it happens, changes everything. It opens the solar system completely. It makes interstellar travel practical for the first time in human history. It transforms us from a species confined to one star to a civilization that can reach others. And that access reveals destinations more incredible than most people imagine. Alpha Centauri sits 4 light-years away. With warp drive at 10 times light speed, that is a 5-month journey. Tau Ceti lies 12 light-years distant, 15 months. Epsilon Eridani, 10 light-years, 1 year. Suddenly, dozens of star systems become reachable within human lifetimes. Astronomers have identified over 5,000 confirmed exoplanets, planets orbiting other stars. Many are gas giants or scorched rocks. But statistical analysis suggests rocky planets in habitable zones exist around perhaps 20% of Sun-like stars. Within 50 light-years of Earth, over 1,000 stars exist. 20% of those might host habitable worlds. 200 potential destinations, 200 planets where liquid water could exist, where life might have evolved. At 10 times light speed, reaching any star within 50 light-years takes 5 years or less, long but achievable, comparable to historical ocean voyages that discovered new continents. Proxima Centauri offers immediate interest, our very closest neighbor at 4.2 light-years. Recent observations confirmed it hosts at least 2 planets. One sits in the habitable zone, Proxima b, a rocky world roughly Earth-sized. We know little about Proxima b. Telescopes cannot resolve surface details. It might be a frozen wasteland. It might be a scorched desert. Or it might have oceans, atmosphere, maybe even life. Warp drive makes finding out possible. Send probes first. Map the surface, analyze the atmosphere, search for biosignatures. If conditions permit, send human explorers later. TRAPPIST. One system sits 39 light-years away. It hosts 7 rocky planets. 3 orbit in the habitable zone. A treasure trove of worlds to explore. At 10 times light speed, 4 years to reach it. Launch in your 20s, arrive in your 30s. Return in your 40s. One lifetime could explore an entire alien solar system. But warp drives faster than 10 times light speed change the equation dramatically. 100 times light speed cuts travel times by 90%. Proxima Centauri becomes a 2-week journey. TRAPPIST, one becomes 5 months. The entire local stellar neighborhood opens for exploration within years instead of decades. Some exoplanets orbit stars hundreds of light-years away, distant, but not impossibly distant anymore. At 1,000 times light speed, a star 500 light-years distant becomes a 6-month journey, difficult but achievable. This raises a profound question. If warp drives make interstellar travel this accessible to us, why have we not detected alien civilizations using similar technology? Where are they? The lack of detected alien signals has puzzled scientists for decades. The universe is old. Life should have emerged elsewhere. Some civilizations should be millions of years more advanced than us. They should be visible, obvious, everywhere. Yet we see nothing. Silence. The galaxy appears empty except for us. Warp drives might explain this, or make the mystery even stranger. The Kardashev scale ranks civilizations by energy consumption. Type 1 harnesses all energy available on their planet. Type 2 harnesses all energy from their star. Type 3 harnesses energy from their entire galaxy. Humanity currently ranks around 0.7. We use a fraction of Earth's available energy. We remain planetary bound, limited. Warp drive technology represents a leap toward Type 1 status. Access to solar system resources enables exponential growth. Asteroid mining provides unlimited metals. Lunar helium-3 fuels fusion reactors. The outer planets offer volatiles and rare materials. Energy and resources cease being constraints. Civilization expands. Population grows. Technology accelerates. But here is the implication that troubles scientists. Any alien civilization that developed warp drives should have expanded across their galaxy by now. Even traveling at modest warp speeds, you could colonize every suitable star system in a galaxy within a few million years. The Milky Way is over 10 billion years old, plenty of time for alien civilizations to arise, develop warp capability, and spread everywhere. We should see evidence, megastructures, artificial signals, modified star systems. We see nothing, which suggests either intelligent life is incredibly rare, or something prevents civilizations from expanding, or we are missing something fundamental. One possibility: warp drives are a dead end. They work theoretically but prove impractical. Every civilization discovers the mathematics, gets excited, then realizes the engineering barriers are insurmountable. They remain confined to their home systems. Another possibility: something destroys civilizations before they achieve warp capability. A great filter, maybe nuclear war, maybe environmental collapse, maybe artificial intelligence. Something that almost always prevents the leap from planetary to interstellar. A third possibility: advanced civilizations deliberately hide. They developed warp drives. They explored the galaxy, but they avoid contact with primitive species like us. We cannot see them because they do not want to be seen. Or perhaps the universe is stranger than we imagine. Maybe warp bubbles cannot sustain life after all. Maybe there is a physics error we have not found yet. Maybe faster than light travel is genuinely impossible, despite the mathematics appearing sound. Our first successful warp flight will not answer these questions immediately, but it starts the process. If we can build working warp drives, then aliens could too. If we successfully colonize other star systems, then aliens should have done the same. Finding alien artifacts on distant worlds becomes possible. Not radio signals traveling for centuries. Physical evidence, ruins, technology, proof that others preceded us. Or we find nothing, empty planets, sterile worlds, no signs that intelligence ever arose except on Earth. That discovery would be equally profound. It would mean we are alone, or first, or the only survivors of some catastrophe that destroyed everyone else. Either answer changes humanity forever, and the timeline for discovering it might be shorter than anyone expected. 2025 through 2035 represents the critical decade, the years when warp drive technology transitions from theoretical to experimental. Current predictions from leading physicists map out the milestones. By 2027, expect functional metamaterial exotic matter generators operating at millimeter scales, still tiny, but producing measurable negative energy density in controlled laboratory conditions. By 2029, scaling to centimeter-sized generators, multiple labs worldwide achieving similar results. Replication confirms the technology works reliably. Commercial interest begins. Private funding supplements government research. 2031 brings the first significant breakthrough: macro-scale exotic matter generation. Devices creating negative energy regions measured in cubic inches, enough to attempt micro-scale warp bubble experiments. The first confirmed warp bubble forms in 2032, not around a spacecraft, around a microscopic particle in a specialized chamber, but confirmed, measured, repeatable. The particle moves faster than physics normally permits. Headlines worldwide announce the achievement. 2033 through 2035 focus on scaling. Larger particles, heavier objects, more stable bubbles, longer durations. Each experiment pushes boundaries. By 2036, maybe 2037, engineers believe they can build a probe-sized warp generator, small spacecraft, heavily shielded, unmanned, ready for the first actual flight test. That first test launches from beyond lunar orbit, clear of Earth's gravity well, clear of space traffic. If something goes wrong, the debris endangers nothing. 10-second activation. The probe vanishes. Sensors track gravitational distortions. 10 seconds later, it reappears 3 million kilometers away. Systems check nominal. Success. Humanity achieved faster than light travel. From there, progress accelerates. Longer flights, distant destinations, eventually crewed missions. By the 2045s, perhaps the first human journey to another star. Alpha Centauri, Proxima b, names that will echo through history like Plymouth Rock. Armstrong's first step, moments when everything changed. But this timeline assumes no major setbacks, no unexpected physics problems, no political decisions to defund research, no accidents that set the program back years. History suggests setbacks are inevitable. The path from theory to application always takes longer than optimists predict. Budget overruns, technical failures, public support wavering when progress stalls. More realistic projections push timelines out. First probe flight maybe 2045. First crewed mission to another star by 2060 or 2070. Still within many lifetimes currently living. Still achievable. And even if it takes longer, the direction is clear. The mathematics works. The physics permits it. The engineering challenges are difficult, but not impossible. Exotic matter generation shows promise. Energy requirements keep dropping. We will build warp drives. The question is not if, the question is when. How soon? Who gets there first? What we discover when we finally reach other stars. The universe waited billions of years for intelligence to arise and look outward, for consciousness to emerge that could ask questions about what lies beyond, for beings who could imagine faster than light travel and then make it real. That moment approaches, closer now than ever before. Within sight of a generation that might live to see it happen, people alive today could witness humanity becoming an interstellar species, could watch the first ships depart for other suns, could hear about worlds circling alien stars where humans walk for the first time. Everything we thought impossible becomes possible. Everything we imagined as distant future becomes near-term reality. The age of warp travel dawns, and nothing will ever be the same. Harold White sat at NASA's Johnson Space Center in 2010, staring at Alcubierre's original equations. The energy requirements looked impossible. Jupiter's mass converted to exotic matter. No civilization could achieve that. But White noticed something. Alcubierre's design used a thin bubble wall, a sharp boundary between normal and warped spacetime. Like a knife edge, sharp transitions require enormous energy to maintain. White asked a different question. What if you made the wall thicker, gentler transitions, space-time curves gradually instead of sharply? Less energy needed to create the same overall effect. He ran the calculations. The numbers dropped. Instead of Jupiter's mass, maybe a smaller planet. Keep refining. Instead of a planet, maybe a large asteroid. Keep going. Maybe a mountain, a building, a truck. By 2012, White published results that shocked the physics community. His modified design, called the Alcubierre White Drive, reduced energy requirements by a factor of billions, not converting Jupiter, converting something the mass of the Voyager 1 spacecraft, around 1,000 kilograms. Confirmed, other physicists verified the mathematics. The refinement worked. Gentler space-time curvature achieves the same result with vastly less exotic matter. But White went further. He changed the bubble's shape. Alcubierre used a sphere, symmetrical, beautiful, mathematically, but not optimal. White proposed a donut shape, a toroidal bubble, like an inner tube surrounding the ship. This geometry distributes stress more evenly across the exotic matter. Each section supports neighboring sections. The structure becomes self-reinforcing. The energy requirements dropped again, perhaps as low as a few hundred kilograms of exotic matter. Still enormous, still beyond current technology, but within conceivable future capability. Then, in 2021, A physicist named Alexei Bobrik published another refinement. He showed you could reshape the bubble dynamically during flight, adjust the geometry based on local spacetime conditions, optimize in real time for minimum energy consumption. This adaptive approach cuts energy needs even further. Early estimates suggested another reduction by half. Maybe 100 kilograms of exotic matter becomes sufficient. Each refinement brings the technology closer to reality. The gulf between impossible and difficult narrows year by year. White's team at NASA built specialized equipment to test pieces of the theory. Interferometers sensitive enough to detect microscopic space-time distortions, field generators that create controlled electromagnetic patterns, sensors monitoring quantum vacuum fluctuations. They called it the White-Juday Warp Field Interferometer. Tests began in 2013. Results remained inconclusive. Some measurements hinted at tiny space-time effects. Others showed nothing. The signals were too weak, too noisy, too close to instrument limits. But the attempt itself mattered. For the first time, engineers built hardware specifically designed to create and measure warp field effects. Not just mathematical speculation, actual experimental apparatus. Budget cuts ended the NASA research in 2015. The lab closed. Equipment was packed away. But the work continued elsewhere. Universities picked up the research. Private companies invested. International teams formed. And everyone built on the Alcubierre White Foundation. The recognition that warp drives do not require impossible energy, just incredibly difficult energy. A crucial difference, because if you create even a tiny warp field, you leave evidence behind, evidence that might be detectable across vast distances. And if we can detect it, maybe we can find signs of alien civilizations using the same technology, or they can find us. When massive objects accelerate, they create ripples in space-time, gravitational waves. Two black holes colliding send waves racing across the universe at light speed. We detect these waves billions of years later using instruments like LIGO. Warp bubbles should create their own signature. A moving region of compressed and expanded space-time generates gravitational disturbances. These disturbances propagate outward. Unlike the bubble itself, the waves travel at light speed. They spread through normal space-time. Theory predicts a distinctive pattern, not the chirp of merging black holes, not the steady hum of rotating neutron stars. Something different, a moving gravitational anomaly. Space-time compression followed by expansion. The signature repeats as long as the bubble exists. Detectors like LIGO might spot this signature, not from warp drives in our solar system, too weak, but from drives operating in nearby star systems, possibly, especially if the drive is large, if it carries significant mass. An alien civilization using warp technology within a few dozen light years might be detectable right now. Their drives would have been active for decades, centuries. The gravitational waves would have reached Earth already. We just need to recognize the pattern. Researchers analyzed existing LIGO data searching for warp signatures. They found nothing definitive, but LIGO was designed to find black hole mergers. Its algorithms filter out other patterns. Something could be hiding in the noise, unrecognized because nobody taught the instruments what to look for. New analysis techniques emerge. Machine learning algorithms trained to recognize warp bubble patterns. Researchers create simulated signatures based on Alcubierre white models. They feed these simulations into AI systems, teach them what to find. Then they turn those trained systems loose on real gravitational wave data, searching, comparing, looking for matches. Unknown whether this approach will succeed. The signal might be too weak, or distorted beyond recognition by distance. Or aliens might use different warp geometries that create different signatures. But the search continues. Beyond detection, gravitational signatures create tracking capability. If we detect a warp drive, we can monitor its trajectory, watch it move between stars, calculate its speed, estimate its size based on signal strength. This works both ways. Any civilization with gravitational wave detectors can spot our warp drives too. The moment we activate the first test flight, we announce our presence to anyone listening. We cannot hide. The signature propagates in all directions. Unmistakable. Some researchers welcome this. We search for alien intelligence. Broadcasting our technological capability might attract attention. First contact becomes more likely. Others worry. We do not know who is listening. Advanced civilizations might view emerging warp-capable species as threats. They might respond with hostility, silencing us before we spread beyond our star system. The concern seems paranoid until you remember the dark forest theory. Maybe the universe is filled with predatory civilizations that destroy competitors. Maybe silence is survival. Maybe the first species to reveal warp capability becomes a target. Confirmed gravitational wave signatures mean we face a choice when we build working warp drives, activate them and announce ourselves, or develop the technology but never use it. Stay hidden, stay safe. Except staying hidden might already be too late, because warp bubbles leave more than gravitational signatures. They might scar space-time itself, creating permanent marks that reveal where drives operated, marks that last for centuries after the bubble collapses. Space-time is not perfectly elastic. Stretch it and it bounces back, usually, but extreme distortions might leave permanent marks, like stretching fabric so hard it tears, or bending metal past its elastic limit. The material remembers. Warp bubbles create extreme distortions, space compressed to fractions of normal distances, space expanded to multiples. The curvature at bubble walls reaches levels comparable to black hole event horizons. When the bubble collapses, space-time should return to flat, normal, but calculations suggest it might not return perfectly. Residual curvature could remain, a ghost of the warp field, faint but measurable. These scars would mark travel routes like highways, follow a path between stars repeatedly, and the scars accumulate, overlap, strengthen. Eventually, that route might show detectable space-time anomalies, even without active warp bubbles present. Theory only. Unknown whether scars actually form. No experiments can test this yet. Creating warp bubbles strong enough to potentially scar space-time remains beyond current capability. But if scarring happens, the implications are profound. Every warp journey leaves evidence, permanent evidence. Future civilizations could map ancient travel routes by detecting these scars, reconstructing who went where millions of years ago. For archaeology, this would be incredible, finding alien travel networks, following them to discover lost civilizations, dead colonies, abandoned worlds that once hosted interstellar societies. For current civilizations trying to hide, scarring becomes a nightmare. You cannot erase the evidence. Every flight marks space-time permanently. Predatory aliens could track those marks back to your homeworld. No escape, no hiding. Scarring might also accumulate environmental damage. If warp travel becomes common, heavily used routes might develop significant space-time distortions. These distortions could affect normal matter passing through, deflecting asteroids, warping planetary orbits slightly, creating gravitational anomalies that compound over millennia. Imagine Earth's solar system in 10,000 years after centuries of heavy warp traffic. Space-time around Earth scarred by millions of departures and arrivals, local space geometry permanently altered. Would this affect Earth's orbit, the Moon's path, satellite trajectories? Unknown. The effects might be negligible, or they might accumulate to dangerous levels. We would need regulations, limits on warp operations near populated systems, designated routes that concentrate scarring in empty space rather than spreading it everywhere. Some physicists propose that space-time scars might actually be useful. They could serve as markers, navigation aids, Follow the scars and you know others have traveled this route safely. Avoid pioneering new paths through uncharted space. Or scars might indicate dangerous regions, areas where previous warp bubbles failed, where space-time collapsed unexpectedly. Smart pilots would avoid heavily scarred regions. Too much residual distortion might destabilize new bubbles passing through. Another possibility involves weaponization. Deliberately create space-time scars to damage enemy territory, warp repeatedly through their solar system, accumulate distortions that disrupt planetary orbits, gravity-based warfare without firing a shot. Defense against this seems difficult. You cannot repair space-time scars easily. The damage persists, accumulates. The only protection would be preventing enemy warp drives from entering your system in the first place. But scarring connects to an even stranger question: whether warp drives allow time travel, whether you can use them to arrive at your destination before you departed, whether causality itself breaks when you exceed light speed. Einstein's relativity links space and time inseparably. Faster than light travel in space means backward travel in time under certain reference frames. You cannot separate them. Move faster than light and causality gets weird. Here is the classic paradox. You depart Earth on Monday, traveling to Alpha Centauri at 10 times light speed. The journey takes 5 months from your perspective. You arrive on Saturday, but to stationary observers watching from a third location, relativistic effects make it appear you arrived on Sunday of the previous week. Before you left, this seems impossible. How can you arrive before departing? Yet the mathematics of special relativity predicts exactly this under specific conditions. Different observers disagree on the order of events when those events involve faster-than-light motion. Warp drives might avoid this problem. You are not moving faster than light through space. The bubble moves. Space itself moves. You remain stationary locally. Different rules might apply, except general relativity, which governs warp drives, connects to special relativity seamlessly. If warp drives allow faster-than-light travel in any reference frame, causality violations become possible somehow. Imagine sending a message via warp drive from Earth to Alpha Centauri, then having someone there send a message back via warp drive to Earth. Under certain velocity combinations and reference frames, the return message could arrive before the original message was sent. This creates information loops, effects preceding causes. You could receive a stock tip from the future, act on it, make money, then send the same tip backward in time to yourself. Where did the information originate? It exists in a loop with no beginning. Physics abhors such loops. They violate causality. They create paradoxes. Something must prevent them. One possibility: the universe forbids warp drive speeds or configurations that would permit causality violations. Whenever you try to set up a causal loop, the warp bubble becomes unstable. It collapses before the paradox can complete. Natural law enforcement built into space-time geometry. Another possibility involves quantum mechanics. Maybe causality loops resolve through many worlds interpretation. Each loop creates a branching timeline. You send the message to a parallel universe version of yourself. No paradox, because the recipient is not quite you, close, but different. A third option suggests warp drives simply do not allow backward time travel at all. The mathematics that predicts time paradoxes might contain errors, assumptions that do not hold for warp bubbles. When you properly account for how warp drives work, the causality violations vanish. Unknown which interpretation is correct. This remains hotly debated in theoretical physics. Some researchers claim they have proven warp drives cannot violate causality. Others claim violations are inevitable. The mathematics gets incredibly complex. Different assumptions lead to different conclusions. Testing would settle this. Build a working warp drive. Attempt to create a causality loop. See what happens. But testing might be dangerous. What if loops are possible and you accidentally create one? What if that breaks something fundamental in local space-time? The safer approach involves theoretical proof. Demonstrate mathematically whether loops can form before building hardware. But decades of work have not produced consensus. Every proof has counterarguments. Meanwhile, engineers planning first warp flights must decide how to handle this. Do they restrict speeds to levels guaranteed safe from causality issues, or do they push limits and hope paradoxes do not materialize? And causality becomes even more complicated when you consider multiple warp bubbles operating simultaneously. Ships traveling together or in opposite directions. What happens when warp bubbles interact? Two warp bubbles traveling parallel courses, separated by a few hundred miles, both moving at 10 times light speed toward the same destination. What happens if they drift too close together? Theory predicts several possibilities. Best case, nothing. The bubbles remain independent. Each creates its own localized spacetime distortion. They pass without interaction. Worst case, catastrophic interference. The compressed spacetime regions overlap. Gravitational forces between them surge. The bubbles attract or repel each other violently. Both collapse in destructive energy releases. Between these extremes lies a fascinating middle ground. The bubbles might synchronize, lock into resonant patterns. Their field oscillations align. Instead of fighting each other, they support each other. Combined bubble formations that travel more efficiently than individual bubbles. Researchers call this convoy warp travel. Multiple ships moving together inside a shared warp envelope, like a fleet sailing together, but on waves of space-time instead of ocean. Advantages are obvious. Shared energy costs. The first ship creates the initial distortion. Following ships ride in its wake using less exotic matter and power. Like geese flying in V formation, each bird after the leader expends less energy. Early calculations suggest convoy formations might reduce individual ship energy requirements by 30 to 40%. Significant savings for long-distance travel. Colony ships, carrying thousands of people, could follow a lead vessel, spreading costs across the fleet. But maintaining formation demands incredible precision. Ships must hold exact positions relative to each other. Drift by even a few feet and you risk bubble collision. The tolerance margins measured in inches despite traveling at multiples of light speed. Quantum entanglement might solve this. Entangled sensors on each ship provide instantaneous position correlation. Automated systems adjust trajectories, microsecond by microsecond, maintaining perfect spacing without conscious pilot input. Another benefit of convoy travel involves redundancy. If one ship's warp generator fails, others might stabilize its bubble temporarily, prevent catastrophic collapse, buy time for emergency repairs or controlled shutdown. Or multiple ships could combine their exotic matter. Instead of each carrying enough for independent travel, they pool resources, create a single massive bubble containing all ships, like a warp-capable space station moving between stars. This scales impressively. 10 ships, each carrying 100 kilograms of exotic matter, could combine into 1,000-kilogram system, enough for a much larger, more stable bubble, one that might sustain higher speeds or longer durations. But problems emerge when bubbles travel in opposite directions. Two ships passing each other while both in warp, head-on encounter at combined speeds of 20 times light. Do they detect each other? Probably not. The compressed space-time ahead of each bubble creates an event horizon. They cannot see what is coming. No warning. No time to react. Do they collide? The mathematics gets uncertain here. Some models predict they pass through each other like ghosts. Each exists in its own disconnected space-time bubble. They never actually interact despite appearing to occupy the same location. Other models predict violent interactions, overlapping space-time distortions creating gravitational shockwaves. Both bubbles destabilizing simultaneously. Ships dropping back into normal space with enormous relative velocity. Collision at significant fraction of light speed. Total destruction. Unknown which is correct. Nobody has tested this. Nobody can test this without building actual warp drives and risking real spacecraft. The safest approach involves traffic control, designated warp lanes like shipping channels. Outbound traffic uses certain routes. Inbound traffic uses separate routes. Crossing paths prohibited. Computer systems plan all flights to ensure adequate separation. This requires coordination across star systems. International agreements. Maybe interstellar agreements once we contact aliens. Rules governing right-of-way. Speed limits in crowded regions. Penalties for violations. Enforcement seems impossible, but the natural consequences might be severe enough. Violate traffic rules, and you risk bubble collision. Your own death becomes the punishment. Strong incentive for compliance. And traffic rules become even more critical if warp technology develops through unexpected routes. If accidental discoveries crack problems that intentional research misses, history suggests this happens more often than people think. Fleming discovered penicillin because mold contaminated his bacterial cultures. Spencer invented microwaves after a chocolate bar melted in his pocket near a magnetron. Viagra was developed as a heart medication before researchers noticed unusual side effects. Scientific breakthroughs often come from accidents, unexpected observations, equipment malfunctions that produce interesting results. Someone noticing something wrong and asking why instead of discarding the data. Warp drive development might follow the same pattern. Researchers working on completely different problems could stumble onto exotic matter generation or space-time manipulation techniques by accident. Consider quantum computing labs. They create exotic quantum states. They manipulate electromagnetic fields in precise patterns. They operate at temperatures near absolute zero, similar conditions to what warp drive research requires. A quantum computer experiment goes wrong. Fields fluctuate unexpectedly. Sensors detect brief space-time anomalies. Researchers investigate. They discover they accidentally created microscopic regions of negative energy. Not intentionally, not predicted, just happened. They replicate the accident deliberately, test variations, map parameters. Within months, they develop reliable exotic matter generation using modified quantum computing hardware. Warp drive research leaps forward accidentally. Or particle accelerators like CERN. They already manipulate high-energy particles, already create extreme conditions. What if a collision experiment produces unexpected gravitational effects? Brief space-time distortions that theory did not predict? Physicists would investigate thoroughly, trying to understand the anomaly. They might discover new physics, new ways to warp space-time, using particle beams instead of exotic matter. Completely different approach to warp drives. Better, cheaper, simpler. Confirmed examples exist of particle physics discoveries that nobody anticipated. Quarks, neutrino oscillations. The Higgs boson showed up where expected, but with properties that surprised researchers. Accidents and surprises drive physics forward constantly. Fusion reactor research offers another possibility. Commercial fusion requires containing superhot plasma using magnetic fields. Those fields reach incredible intensities. They manipulate matter in extreme conditions. What if a fusion containment field configured in a specific geometry creates Casimir-like effects at larger scales? What if the magnetic field patterns suppress quantum vacuum fluctuations in controllable ways? Accidental exotic matter generation from fusion research. Even materials science could produce breakthroughs. Labs develop new metamaterials for electronics, for optics, for mechanical applications. Someone creates a material with unusual quantum properties. It happens to manipulate vacuum fluctuations in useful ways. Warp drive application was never the goal, but the material works anyway. History shows that technology often emerges from unexpected directions. The internet started as military research. GPS came from navigation requirements for nuclear submarines. Touchscreens were invented decades before smartphones made them ubiquitous. Warp drives might follow similar paths. The breakthrough might come from medical imaging research, from computer chip manufacturing, from attempts to build better solar panels. Someone working on a completely different problem accidentally creates the exact conditions needed for exotic matter generation. This matters because it suggests we might be closer to warp capability than organized research indicates. Unknown labs working on unrelated projects could achieve critical discoveries without recognizing their importance immediately. Years might pass before someone connects the dots. It also suggests multiple groups might discover warp technology simultaneously through different routes. Competition would intensify. Patents become meaningless if several teams develop working drives independently. The technology spreads rapidly. Unavoidably, governments might try to classify warp research. Keep it secret. Military advantage. But if discoveries happen accidentally in civilian labs worldwide, classification fails. The cat escapes the bag. And once one group demonstrates working warp technology, everyone else rushes to replicate it. Reverse engineering accelerates development. Within years, multiple nations and companies operate warp-capable vehicles, which raises questions about fuel sources. Where exotic matter comes from might matter less than whether natural sources exist. Whether the universe provides warp drive fuel for free, hidden in the fabric of space itself. Something is pushing the universe apart. Galaxies accelerate away from each other. The expansion rate increases over time. Physicists call this mysterious force dark energy. We do not know what dark energy is. We cannot detect it directly. We see its effects. The universe expanding faster than gravity alone would permit. Some form of energy pervades space, everywhere. Constant density, pushing outward. Dark energy might be exotic energy. The quantum vacuum itself might naturally contain negative pressure. Repulsive gravity, exactly what warp drives need. If this connection is real, it changes everything. You would not need to create exotic matter. You would harvest it from space itself. Dark energy exists everywhere in enormous quantities, enough to accelerate the entire universe, surely enough to power a few warp bubbles. The challenge becomes extraction. How do you collect dark energy? It pervades all space uniformly. You cannot concentrate it, you cannot bottle it. It simply exists as a property of vacuum. But maybe you can manipulate it. Electromagnetic fields might interact with dark energy in ways we have not discovered yet. Specific field configurations might amplify or redirect it, channel it, focus it where needed. Theory only. Unknown whether this actually works. Dark energy remains poorly understood. We barely know it exists. We certainly do not know how to manipulate it. Yet some researchers pursue this direction actively. They propose experiments using superconducting magnets arranged in specific geometries, looking for tiny changes in local dark energy density, searching for any interaction between electromagnetic fields and whatever dark energy actually is. Results so far show nothing. But negative results do not prove impossibility. Maybe they are looking in wrong ways, using wrong field strengths, wrong geometries, wrong detection methods. If dark energy can be harnessed, warp drives become almost trivial. No exotic matter manufacturing, no massive energy investments. Just tap into the existing background energy field. Turn it on, travel anywhere, turn it off. The universe becomes a gas station, dark energy everywhere, unlimited fuel, free for the taking. This might explain why we do not detect alien civilizations. Maybe they discovered dark energy harvesting centuries ago. They travel between galaxies easily. They expanded far beyond electromagnetic communication range. We cannot see them because they operate at scales incomprehensibly vast. Or maybe dark energy harvesting is impossible. Maybe the connection between dark energy and exotic matter is superficial. Similar properties, but different sources. You cannot use one as the other. determining which requires better understanding of dark energy itself. Cosmology research might unlock warp drives accidentally. Studying why the universe expands might reveal how to surf that expansion deliberately. Another cosmic phenomenon might contribute: cosmic inflation. The brief period immediately after the Big Bang, when space expanded faster than light. Whatever drove inflation might be related to whatever enables warp drives. If we understand inflation mechanisms, we might learn to reproduce them, create localized inflation bubbles, not universe scale, ship scale. The bubble inflates space behind you and contracts space ahead. Warp drive through inflation physics. Speculative, highly theoretical, but not completely crazy. Inflation happened. Space can expand faster than light under right conditions. Those conditions occurred naturally once. Maybe technology can recreate them. All of this assumes no hard speed limits exist for warp travel. But maybe limits do exist. Maybe you cannot warp arbitrarily fast. Maybe the universe imposes a ceiling. Light speed is a hard limit for normal motion through space. But warp drives bypass that limit by moving space itself. So what stops a warp bubble from moving at any speed? 1,000 times light speed? 1,000,000? Infinite? The mathematics initially suggests no limit. Alcubierre's equations work at any speed. You just adjust how sharply you compress and expand spacetime. Want to go faster? Compress more. The equations balance. But deeper analysis reveals problems. At extreme speeds, quantum effects become significant. The Heisenberg uncertainty principle limits how precisely you can define spacetime geometry at small scales. Above certain speeds, the warp bubble geometry becomes quantum uncertain. When geometry becomes uncertain, stability collapses. The bubble cannot maintain precise shape. It fluctuates. Those fluctuations grow. The bubble tears itself apart. Calculations suggest this quantum instability limit kicks in somewhere between 1,000 and 10,000 times light speed. Maybe. The math gets incredibly complex at this level. Different assumptions give different answers. Another limit comes from Hawking radiation. Faster bubbles generate more radiation. At some speed, the radiation intensity becomes so extreme it destroys the ship instantly. Or it drains energy from the bubble faster than you can supply it. The bubble collapses from energy loss. This radiation limit might be lower than the quantum limit, perhaps a few hundred times light speed. Unknown. Nobody has tested this experimentally. A third potential ceiling involves spacetime itself. Maybe spacetime has a maximum deformation rate. Compress it too quickly, and it resists. Like trying to compress water, it is nearly incompressible. Push too hard and you just create shock waves instead of smooth compression. If spacetime has similar properties, extreme warp speeds might hit a wall. The space ahead refuses to compress further. The space behind refuses to expand more. You reach the material limit of what spacetime can do. Theory predicts spacetime should be infinitely deformable. But theory might be wrong. The universe might have properties we have not discovered, hard limits that emerge only at extremes. Testing these limits requires building working warp drives first, then pushing speed gradually higher, seeing where problems emerge. Which limit you hit first tells you what physics you need to understand better. Practically, even modest warp speeds make interstellar travel feasible. 10 times light speed reaches nearby stars within years. 100 times light speed reaches distant stars within decades. You do not need 1,000 times light speed for useful exploration. But galaxy-scale travel requires higher speeds. The Milky Way spans 100,000 light-years. At 100 times light speed, crossing it takes 1,000 years. Possible but barely. Multiple generations. At 10,000 times light speed, crossing the galaxy takes 10 years. Suddenly feasible. You could explore the entire galaxy within a human lifetime. If speed ceilings exist below that level, galaxy-wide civilization becomes difficult. You stick to local neighborhoods, maybe 10,000 light-years radius. Your civilization remains regional, never truly galactic. But if no ceiling exists, or if it is high enough, then everything opens. Not just galaxy-wide, but intergalactic travel becomes possible. Andromeda Galaxy sits 2.5 million light-years away. At 10,000 times light speed, that is 250 years. Challenging but achievable with generation ships. The speed question determines what kind of spacefaring civilization humanity can become: local, galactic, or universal. And the answer might depend on something nobody has seriously considered yet. What happens inside the bubble? Whether acceleration affects you despite the warp field. The promise of warp drive sounds perfect. You stand still inside the bubble while space moves around you. No acceleration, no g-forces, no discomfort. You could travel at 1,000,000 times light speed and feel nothing. Except that might be oversimplified. The bubble itself must accelerate when you activate it. 0 speed to 10 times light speed in seconds. That transition involves incredible acceleration of the bubble structure. Does any of that transfer to the ship inside? Theory says no. Inside the bubble, space-time remains flat. Local physics operates normally. You should feel nothing. Like standing in an elevator. When the elevator accelerates, you feel forces. But if you float weightless inside, acceleration does not affect you the same way. Except this analogy breaks down. Elevators accelerate through space. Warp bubbles accelerate by changing space. Different mechanism, maybe different consequences. Some physicists worry about tidal effects during bubble formation. The bubble forms around the ship over milliseconds. During that brief time, different parts of the ship might experience different space-time curvatures. Your head versus your feet, front versus back. These differential curvatures create tidal forces, stretching forces, potentially strong enough to damage the ship structure, or injure crew members, or disrupt sensitive equipment. Calculations suggest these effects should be minimal if bubble formation happens smoothly. Gradual ramp up over seconds instead of instant activation. Tidal forces spread out, become manageable. But what about turbulence? Space is not perfectly empty. Gravitational fields from distant stars, magnetic fields, dark matter, quantum fluctuations. As your bubble passes through these irregularities, does the geometry ripple? Think of sailing a boat. Smooth water gives a smooth ride. Choppy water creates constant motion, pitching, rolling, uncomfortable, potentially dangerous in storms. Space-time might have similar roughness, usually smooth, but occasionally you hit a gravitational wave or pass through a region of higher dark matter density. The bubble responds, flexes. That flex might translate into forces felt inside the ship. Unknown how significant these effects are. Simulations suggest they should be small. Real testing would involve building a warp drive and seeing what astronauts actually experience. Engineers plan for worst case, acceleration couches for crew members, restraints, medical monitoring. If inertial dampening is not perfect, at least minimize injury risk. Another concern involves sudden stops. What if the bubble collapses unexpectedly? You are traveling at 10 times light speed. Suddenly, the bubble vanishes. Do you decelerate instantly back to normal speeds? That would be catastrophic, like hitting a wall at impossible velocity. Everything inside the ship becomes paste. Instant death. But physics suggests this should not happen. When the bubble collapses, you do not stop. You continue moving at whatever velocity you had in local spacetime, which was near zero. You were stationary inside the bubble. Collapse just returns you to normal space at low relative velocity. The ship survives. Crew survives. You just end up wherever you were when collapse occurred, probably nowhere near your destination. Stranded, but alive. Theory predicts this. Unknown if theory is complete. Maybe there are transition effects we have not calculated. Brief but intense forces during bubble collapse, enough to damage systems or injure people. Testing must proceed carefully. First tests with unmanned probes. Measure everything. Look for unexpected acceleration signatures, gradual scale-up to larger objects, animals, eventually humans. Only after proving safety beyond reasonable doubt should humans enter warp bubbles. The risk is too high otherwise. One miscalculation and you kill everyone aboard. But if inertial dampening works as theory predicts, warp drives become the safest form of high-speed travel ever developed. No acceleration stress, no collision risk at normal speeds. Just smooth, comfortable journeys across impossible distances, which connects to another theoretical possibility, one that sounds completely insane until you examine the mathematics closely. Bubbles that are bigger on the inside than the outside. Chris van den Broek published a mind-bending modification to Alcubierre's design in 1999. His version creates a warp bubble with bizarre geometry. Microscopic exterior, macroscopic interior. From outside, the bubble looks tiny, maybe a few feet across, but inside, the bubble contains a region of flat spacetime large enough for an entire spacecraft, or a space station, or a small city. This seems to violate conservation of volume. How can something be bigger on the inside? But general relativity permits it. Space can curve in ways that create this effect, like a wormhole, small entrance, large interior, different geometry. The van den Broek approach solves several problems simultaneously. Smaller exterior means less space-time distortion, less exotic matter needed, lower energy requirements. You create a bubble around a ship-sized interior using exotic matter quantities appropriate for a person-sized exterior. The reduction in energy needs is dramatic, perhaps a factor of 100 or more. Instead of hundreds of kilograms of exotic matter, maybe a few kilograms suffice. Smaller exterior also reduces collision risks. A 10-foot bubble is easier to navigate around obstacles than a 300-foot bubble, less likely to hit debris, less gravitational disruption to nearby objects. But creating this geometry is far more complex than standard Alcubierre bubbles. You need exotic matter arranged in very specific configurations, multiple layers, precise density gradients. Any error and the interior collapses or the exterior expands to match it. The mathematics works beautifully. The engineering looks nightmarish. You need exotic matter with varying properties at different distances from the ship. Materials that exist even less likely than uniform exotic matter. Some researchers argue van den Broek bubbles are technically possible, but practically impossible. The precision requirements exceed anything achievable with real-world manufacturing. Quantum uncertainties alone would prevent achieving the necessary tolerances. Others remain hopeful. Advanced metamaterials might work. Structures engineered at atomic scales could create the required exotic matter gradients. Not easy, but may be possible with sufficient technology development. Testing van den Broek geometries could happen at small scales first. Create a bubble containing a cubic millimeter of interior space inside a cubic micron exterior. Microscopic, but enough to prove the concept. If that works, scale up gradually. Bigger interiors, always keeping exteriors small. Eventually, a bubble containing a warehouse-sized space inside a car-sized exterior. The applications extend beyond warp drives. Van den Broek bubbles could create portable enclosed spaces, carry a house that fits in your pocket, storage containers with impossible internal volumes, starships that look tiny from outside but contain vast interiors. Unknown whether any of this is achievable, the theory is solid. The engineering might be impossible, or we might crack it through persistent research and clever solutions. Another potential exists within natural spacetime features, cosmic strings and other exotic structures predicted by physics. Maybe these structures create ready-made warp channels, highways through space that require no exotic matter generation. Cosmic strings are theoretical defects in spacetime, like cracks in ice. They formed during the early universe, when different regions underwent phase transitions at slightly different times. Where these regions met, strings formed. one-dimensional defects stretching across space. If cosmic strings exist, they have incredible properties. Mass concentrated into lines thinner than atoms but stretching for light years. The gravitational field around a cosmic string warps spacetime intensely. Not like planets or stars. Different geometry entirely. Travel near a cosmic string and spacetime curves in unusual ways. Some theoretical models suggest you could use this curvature for faster-than-light travel. Approach a cosmic string from the right angle. Let its natural spacetime distortion accelerate you. No warp drive needed. No exotic matter. Just exploit existing cosmic infrastructure. The challenge is finding cosmic strings. Nobody has detected them yet. They are predicted but unconfirmed. They might not exist at all, or they might be rare, or common but difficult to detect. If cosmic strings exist, and if they are numerous enough, they could form a natural network, travel routes connecting different parts of the galaxy, highways that any civilization could use. You just need to find them and learn to navigate them. This might explain the Fermi paradox differently. Maybe advanced civilizations discovered cosmic string networks eons ago. They use those networks exclusively. No artificial warp drives needed. They travel along cosmic strings invisible to our telescopes. We cannot detect them because we are looking for wrong signatures. Beyond cosmic strings, other natural structures might assist warp travel. Regions where dark matter concentrates. Areas where space is already curved by massive objects. You could surf these existing distortions. Add minimal additional warping to achieve faster than light speeds. Think of it like sailing. You can row a boat anywhere using pure effort, or you can raise sails and use wind. Wind exists naturally. You harness it. Travel becomes easier. Space-time might have similar features. Currents, flows, structures that assist movement if you know how to use them. Discovering and mapping these features could be as important as developing warp drive technology itself. Early interstellar explorers would search for these natural highways, chart them, build databases. Over time, preferred routes emerge. The cosmic equivalent of trade routes. Paths through space where faster-than-light travel requires less energy. Safer, faster. But using natural structures raises questions about energy balance. If you extract energy from space-time distortions to power your journey, where does that energy come from? Does the universe keep accounting? Do you have to repay what you borrow somehow? Conservation of energy is fundamental physics. Energy cannot be created or destroyed, only transformed. When you use energy, it comes from somewhere. When you create exotic matter for warp drives, where does that energy come from? The obvious answer, you put energy in, create exotic matter through Casimir effects or other methods. You supply the energy to create negative energy states. Input balances output, but warp drives might borrow energy from space-time itself. Compress space ahead, expand space behind. You are not creating new energy. You are redistributing existing space-time energy, borrowing it temporarily. When the bubble collapses, does space-time recover that energy? Or does the universe lose track? Energy conservation might work locally, but fail globally. Some theories suggest space-time must balance its books eventually, maybe not immediately, but over time, the energy you borrowed to create the warp bubble gets repaid somewhere, somehow. This repayment could happen through Hawking radiation. The bubble emits energy during travel. That emission might represent space-time, reclaiming what you borrowed. Perfect balance. Nothing lost overall. Or repayment happens when the bubble collapses. Sudden energy release, exactly equal to what you borrowed. The ship survives if this energy radiates safely away, or the ship vaporizes if the energy concentrates locally. Unknown which model is correct. Multiple theories propose different energy accounting methods. All make sense mathematically. None can be tested without actual warp bubbles. A darker possibility exists. Maybe energy conservation does not apply strictly to warp drives. Maybe you can extract energy from space-time permanently, create it from nothing by clever manipulation of quantum vacuum. This would be revolutionary. Infinite energy, free energy, power anything using warp drive principles, not for travel, for energy generation, solve Earth's energy crisis, forever. Except if this works, why does not the universe already do it naturally? If energy can be created from vacuum, why do stars burn fuel? Why does anything require energy input? Either the universe prevents this somehow, or the accounting is more subtle than we understand, or there are penalties for cheating energy conservation that we have not discovered. Those penalties might include black hole formation. If you extract too much energy from space-time, maybe the local region collapses into a singularity, a micro black hole, tiny but deadly. Black holes form when mass compresses past a critical density, the Schwarzschild radius, smaller than that, and gravity becomes so strong that nothing escapes, not even light. For stellar mass black holes, this process is well understood. Stars collapse, black holes form, but at microscopic scales, the physics gets weird. Quantum mechanics suggests tiny black holes should evaporate rapidly through Hawking radiation. A black hole, the mass of a mountain, evaporates in seconds. One, the mass of a car, evaporates in microseconds. Smaller ones vanish even faster. But what if warp bubble collapses create conditions for micro black hole formation? The extreme space-time curvature at bubble walls approaches black hole levels. If collapse happens wrong, that curvature might not dissipate smoothly. It might concentrate. A region smaller than an atom experiences curvature exceeding the Schwarzschild threshold. A micro black hole forms, mass energy equivalent to a few kilograms. It evaporates in nanoseconds through violent Hawking radiation bursts. Gamma rays, X-rays, enough energy to vaporize the ship. Theory only. Unknown if this can actually happen. The conditions required are extreme. Bubble collapse would need to be catastrophically wrong. Instant failure of all stabilization systems simultaneously. Unlikely, but not impossible. Murphy's law applies. If something can go wrong in the worst possible way, eventually it will. Engineers design multiple safeguards. Redundant collapse mechanisms that prevent sharp transitions. Sensors that detect instability early. Automatic systems that smooth the collapse over seconds instead of microseconds. Each safeguard reduces the risk of micro black hole formation, but zero risk is impossible. Some residual chance always remains. Early warp missions carry this danger. Astronauts must accept it. Like early aviation pioneers accepting crash risk, progress requires some people willing to take calculated risks. Another black hole concern involves accidental creation during normal warp travel. What if sustained warp bubble operation slowly accumulates space-time stress? After months of continuous warping, does that stress reach critical levels? Does a black hole form spontaneously from cumulative damage? Calculations suggest this should not happen. The stress should dissipate continuously, no accumulation. But calculations might miss something subtle, some non-linear effect that only appears after extended operation. The first long-duration warp flight will test this unknowingly. If crew survives, the concern vanishes. If they do not, we learn the hard way that extended warp operation has hidden dangers. And hidden dangers might extend to who operates these drives, because warp capability in human hands might be the ultimate test of a species' maturity. Are we ready for this technology, or will we destroy ourselves with it? Someone will go first. Some person will step aboard the first warp-capable ship cleared for human occupancy. They will activate the drive. They will vanish into disconnected space-time. They will either survive or become the first warp travel casualty. Who volunteers for that risk? What kind of person says yes to odds nobody can calculate accurately? History provides examples. test pilots who flew experimental aircraft, astronauts who rode early rockets, cosmonauts who accepted one-way missions, people who value discovery and progress more than personal safety. The selection process would be rigorous. Physical screening ensures candidates can withstand potential G-forces during bubble transitions. Psychological evaluation confirms mental stability under isolation and stress. Technical training teaches operation of unfamiliar systems, but beyond qualifications, volunteering requires specific personality traits: comfort with uncertainty, acceptance of mortality, deep curiosity that outweighs fear, belief that their risk serves humanity's future. These people exist, always have. The same drive that pushed humans out of Africa, across oceans, into space. Some individuals feel compelled to explore, to go where nobody has been, to test boundaries. Warp Drive volunteers would become legendary. If they succeed, they are heroes, first humans to travel faster than light, names remembered for millennia. If they die, they are martyrs. Their sacrifice advances knowledge. Either way, immortality of a sort. Agencies would receive thousands of applications, far more volunteers than needed. Selecting who actually goes becomes agonizing. So many willing, so few slots available. Selection criteria must balance capability with representation. You want the best qualified people, but also diversity, different backgrounds, different expertise, a team that brings varied perspectives. Age matters too. Send young people and you maximize future utility if they survive. They could participate in multiple missions, decades of exploration ahead. Send older people and you minimize life years lost if they die. Ethical calculation, cold but necessary. Family status creates dilemmas. Send someone with children and you risk orphaning kids if things go wrong. Send someone without close family and you minimize others' grief. But is that fair to either group? Some argue only volunteers without dependents should qualify. Others argue that restriction unfairly discriminates. The debate continues, without clear resolution. Training would take years. You cannot rush this. Volunteers must understand every system, practice every contingency, drill emergency procedures until they become automatic. Physical conditioning to peak levels, team bonding to ensure crew cohesion under stress. By launch day, these volunteers would be the most thoroughly prepared humans who ever lived. Still, they would face unknowns, situations training cannot anticipate, decisions only they can make in the moment. And their success or failure determines more than their own fate. It determines how quickly warp technology spreads, how society adapts, how economies restructure when distance stops mattering. Because working warp drives do not just enable space travel, they destroy every distance-based economic model. Distance costs money. Shipping products across oceans takes time and fuel. Flying cargo across continents is expensive. These costs shape where factories locate, where people live, how trade flows. Warp drives eliminate distance costs. Travel from Earth to Alpha Centauri at 10 times light speed takes 5 months. Travel from New York to London takes seconds. Distance becomes irrelevant. Manufacturing could happen anywhere. Cheap labor in distant countries, warp raw materials there in minutes. Transport finished goods back instantly. No shipping delays, no cargo vessels, no warehouses for transit inventory. The entire logistics industry transforms overnight. Shipping companies obsolete, airlines obsolete, trucking companies obsolete, for anything traveling far enough that warp makes sense. Millions of jobs disappear. New jobs emerge but require different skills. Operating warp gates, maintaining exotic matter generators, coordinating instantaneous transportation networks. Real estate value restructures completely. Beachfront property loses premium when any home can reach any beach in seconds. Remote wilderness becomes accessible as downtown. Location advantages vanish. Cities might depopulate. Why live in expensive urban centers when you can walk to work in moments? Live on mountaintops, islands, space stations. Commute to Earth-based jobs daily. Or cities become denser. If travel is free, people choose homes based purely on preference and price. Cheaper rural areas attract exodus. Cities must offer something besides location to retain residents. Global inequality might decrease or increase dramatically. Decrease because resources from asteroids become accessible to all nations. Space mining eliminates scarcity. Metals, rare earths, volatiles, all abundant. Increase because nations with warp technology dominate those without. Resource collection requires warp-capable ships. Developing nations cannot compete. The gap widens. International relations transform. Geography stops defining borders when anyone can warp anywhere. How do you patrol borders against people who can appear anywhere instantly? Immigration control becomes impossible. Nation-states might become obsolete. Why maintain separate countries when location is meaningless? Or nations splinter further? Communities define themselves by culture and values rather than geography. Currency systems face disruption. What backs currency value when resources are unlimited? When production can happen anywhere? When trade barriers cannot function because goods warp past customs? Some economists predict economic utopia. Abundance eliminates poverty. Everyone accesses unlimited resources. Scarcity ends. Others predict chaos. Existing power structures collapse. Wars over warp technology access. Social upheaval as old systems fail and new ones emerge unclear. Unknown which vision is accurate, probably something between extremes. Economic transformation happens gradually as warp technology scales up. Initial high costs limit access. Years pass before effects cascade fully through society. But the transformation is inevitable. If warp drives work, you cannot maintain distance-based economics when distance stops existing practically. Every system built on geographical separation must adapt or die. And adaptation requires wisdom, foresight, planning, the kind of long-term thinking humanity struggles with but desperately needs, because we are building technology that could save us or destroy us. The outcome depends entirely on how we use it.